Did you know that the reality we perceive every single day, the stars we gaze at, the planets we study, the galaxies that stretch across the night sky, all of that makes up just 5% of the entire universe? The rest, a staggering 95%, is completely invisible to us, made of mysterious substances we call dark matter and dark energy. It's a fact that sounds more like science fiction than actual science, and yet it's the very foundation of our modern understanding of the cosmos. And that's just the beginning. The universe is far stranger, more complex, and more breathtaking than we ever imagined, filled with truths so surprising they challenge not only what we know, but how we think about reality itself. What if I told you that some of the most fundamental ideas we hold about space, time, and existence might be completely wrong? That black holes could be gateways to other universes, that time might not flow in one direction, or that there could be an infinite number of versions of you reading this very sentence right now in parallel realities. These aren't just wild guesses, they're real theories being explored by scientists right now, grounded in math and observation, yet so unbelievable they stretch the limits of human imagination. And in this video, we're going to explore 30 of these mind-bending truths, each one peeling back another layer of the cosmic mystery, revealing a universe that is more wondrous, more bizarre, and more humbling than anything we've ever dreamed of. So get ready to have everything you thought you knew turned upside down. We're about to journey through the farthest reaches of space and the deepest laws of physics, exploring everything from the possibility of multiple dimensions to the shocking fate that awaits our cosmos billions of years from now. This isn't just a list of facts, it's an invitation to see the universe in a whole new way, to reconnect with that childlike sense of wonder we all once had when we first looked up at the stars and asked, "What's out there?" By the time we're done, your understanding of reality won't just be expanded, it might be completely transformed. Let's begin. Truth number 1 on our journey into the unbelievable might just be the most humbling reality of all. That beautiful star-filled night sky we all admire, that's the universe's greatest magic trick. It's an illusion, a grand performance where almost all the actors are hidden in the shadows. You see, everything our eyes can see and our telescopes can detect, every single star, planet, nebula, and galaxy, accounts for a mere 5% of the total content of the universe. The other 95% is completely invisible, made of two mysterious and powerful forces we call dark matter and dark energy. Think of it like this: if the universe were an ocean, everything we've ever known and studied would be nothing more than a thin layer of foam on the very surface. The real depth, the vast and powerful currents moving beneath, are made of stuff we cannot see, touch, or even fully comprehend. So what exactly is this hidden universe? Let's start with dark matter. We know it exists not because we can see it, but because we can see its incredible gravitational effects on the things we can see. Back in the 1930s, an astronomer named Fritz Zwicky was studying a huge cluster of galaxies and noticed something bizarre. The individual galaxies were moving so fast that the gravity from all their visible stars and gas should not have been nearly strong enough to hold the entire cluster together. By all rights, the cluster should have flown apart, scattering galaxies across the cosmos. The fact that it didn't meant only one thing: there had to be a huge amount of invisible matter in there, providing the extra gravitational glue to keep everything bound together. This unseen mass became known as dark matter. Today, we see its fingerprints everywhere. The outer stars of spiral galaxies orbit their centers far too quickly, again suggesting they're being whipped around by the gravitational pull of an enormous, invisible halo of dark matter enveloping each galaxy. We can even map its distribution through an effect called gravitational lensing, where the gravity of dark matter warps the very fabric of space-time itself, bending the light from distant galaxies behind it like a cosmic magnifying glass. These observations have revealed that dark matter forms a gigantic, intricate cosmic web, a scaffolding upon which all the visible galaxies are built. Without it, galaxies like our own Milky Way simply wouldn't exist. And then there's its even more mysterious counterpart, dark energy. While dark matter uses its gravity to pull the universe together, dark energy is doing the exact opposite. It's pushing the universe apart at an ever-increasing rate. This shocking discovery in the late 1990s completely overturned our expectations. Everyone thought the expansion of the universe following the Big Bang should be slowing down over time because of gravity's relentless pull. But when two separate teams of astronomers measured distant exploding stars to gauge this cosmic slowdown, they found the opposite was true. The expansion wasn't slowing down at all, it was speeding up. Something was actively fighting against gravity and winning. That something is dark energy, a repulsive force that seems to be an inherent property of empty space itself. It is the dominant force in our universe dictating its ultimate fate, and we have almost no idea what it is. So here we are, living in a universe where 95% of its contents are a total mystery. We are surrounded by an invisible ocean of dark matter that sculpts the cosmos and filled with a strange dark energy that is relentlessly stretching the very vacuum of space. We know they are there, shaping everything from the largest structures to the ultimate destiny of existence, yet they remain just beyond our grasp, the universe's greatest and most profound secret. Yet if you think that's a mind-bending truth about the cosmos, wait until we peel back another layer of reality itself. Truth number 2 takes us from the vast, hidden architecture of the universe to the very fabric of our existence, time. And the most shocking thing we've learned is that time is not the constant, universal heartbeat we perceive it to be. It's fluid, it's malleable, it's relative. This isn't a philosophical idea, it's a fundamental law of physics proven beyond any doubt, and it comes from one of the greatest minds in history, Albert Einstein. His theory of relativity tells us that time literally flows at different rates depending on two things: how fast you're moving and how strong the gravity is where you happen to be standing. The faster you move through space, the slower you move through time, and the stronger the gravity you experience, the more time itself will slow down for you. This means that if you could take a journey on a super-fast spaceship and return to Earth, you would find that less time has passed for you than for everyone who stayed behind. You wouldn't just feel younger, you would literally be younger by a measurable amount. Your clock and your biological aging would have genuinely ticked more slowly. We don't even need a far future spaceship to see this in action. We see it every single day with a technology millions of us rely on, the Global Positioning System, or GPS. The satellites that make GPS possible are orbiting our planet at thousands of miles per hour. According to Einstein's special theory of relativity, because they're moving so fast relative to us on the ground, the atomic clocks on these satellites actually run slower. They lose about 7 millionths of a second each day because of their speed. But there's another effect at play. These satellites are also much farther from Earth's gravitational pull than we are. According to Einstein's general theory of relativity, being in this weaker gravitational field makes time run faster for the satellites. This effect is even stronger, causing the satellite clocks to gain about 45 millionths of a second per day. When you combine these two astonishing effects, time running slower from speed but faster from weaker gravity, the satellite clocks ultimately gain a net total of about 38 millionths of a second each day. That might sound incredibly tiny, but for a system that requires nanosecond precision to calculate your position accurately, that error would accumulate rapidly. Without correcting for Einstein's relativity, the GPS in your phone or your car would be off by about 6 miles every single day. The entire system would become useless in a matter of minutes. So, engineers must pre-program the satellite's clocks to tick at a slightly slower rate before they are even launched, just to compensate for the warping of time they will experience in orbit. Your ability to navigate is living, daily proof that time is not absolute. This concept stretches our imagination to its limits. It means there is no single now for the entire universe. Your now and the now of someone on a distant planet or traveling at a different speed are not the same. The flow of time is a personal experience shaped by your own journey through the cosmos. It shatters the Newtonian idea of a universal clock ticking away in the background of space and replaces it with a far more beautiful, intricate, and interconnected cosmic tapestry where space and time are woven together into a single dynamic fabric that can be bent, stretched, and twisted. But if the true nature of time leaves you feeling unmoored, just wait until we try to wrap our heads around the sheer, incomprehensible scale of the cosmos. This brings us to truth number 3, a statement you may have heard before but whose true weight is almost impossible to grasp. There are more stars in the observable universe than there are grains of sand on all the beaches and in all the deserts of our entire planet. This isn't just a poetic comparison, it's a cold, hard mathematical fact that reveals the staggering vastness of the space we inhabit. Let's break down the numbers starting right here at home. How many grains of sand are we actually talking about? Geologists and mathematicians have actually done the calculations. They estimate that the Earth holds roughly 7.5 quintillion grains of sand. Now, a quintillion is a 1 followed by 18 zeros. To write that out, it looks like this: 7 quintillion, 500 quadrillion grains. It's a number so large it feels abstract, completely divorced from our daily experience. You could spend your entire life counting individual grains on a single beach and barely make a dent. Now imagine that number representing every single grain on every shoreline, in every dune, and buried deep beneath every ocean floor across the entire globe. It is an amount that defies human imagination, and yet that number is utterly dwarfed by the census of the heavens. Our cosmic journey begins not with sand but with galaxies. For most of human history, we believed our Milky Way was the entire universe. We now know it is just one of countless cities of stars. Current estimates suggest the observable universe contains somewhere between 100 billion and 200 billion galaxies. And that's just the ones we can see. Now, let's take a fairly average galaxy, not even one of the largest, something similar to our own Milky Way. It contains somewhere between 100 billion and 400 billion stars. So to find the total number of stars, you perform the most humbling multiplication problem imaginable. You multiply the number of galaxies by the number of stars per galaxy. Even using the most conservative estimates, 100 billion galaxies, each with 100 billion stars, the result is a number so colossal it needs a new name: 10 sextillion stars. That's a 1 followed by 22 zeros. If we use the higher estimates, we're looking at a number approaching 200 sextillion stars. Now, compare that to our 7.5 quintillion grains of sand. A sextillion is 1,000 times larger than a quintillion. This means that for every single grain of sand on Earth, there are thousands upon thousands of stars shining in the cosmos. Thousands of entire suns, each with the potential to host its own family of planets, for every single tiny speck of sand you have ever held in your hand. To truly appreciate this scale, let's try a thought experiment. Picture yourself standing on a familiar beach. You bend down and let the fine, warm sand trickle through your fingers. Each grain is unique, a tiny world of its own. Now, in your mind's eye, zoom out, see the entire beach, then the coastline, then the continent, until you see the whole Earth as a beautiful blue marble. All its sand combined is that 7.5 quintillion number. Now, zoom out further, see our solar system, then our galaxy, a swirling disk of hundreds of billions of stars. Now push past the Milky Way out into the intergalactic void. You see other galaxies, first by the dozen, then the 100, then the 1,000. Soon you're looking at a Hubble Deep Field image, a patch of sky that seemed empty to our eyes but is in fact packed with thousands of galaxies, each a faint smudge containing hundreds of billions of stars. And this view is repeated in every direction for billions of light years. The numbers are so vast they become meaningless to our brains, which evolved to understand the world immediately around us. We can say the words 10 sextillion stars, but we cannot truly feel it. The comparison to sand is the best anchor we have, a way to tether an impossible cosmic concept to something tangible from our world. And in doing so, it does more than just state a fact. It delivers a profound sense of perspective. It tells us that our planet, for all its beauty and complexity, is an infinitesimally small speck in a universe of unimaginable grandeur. Every hero who ever lived, every empire that ever rose and fell, every joy and every heartbreak in human history has occurred on a single grain of sand in a cosmic ocean of stars. And while we grapple with the sheer, humbling scale of the cosmos, it's easy to forget that even the most familiar objects in our sky hold deep, dynamic secrets of their own. This brings us to truth number 4, a quiet but constant change happening right before our eyes, or rather, just beyond them. Our own moon is slowly leaving us. Each year, the moon drifts about 3.8 centimeters farther away from Earth. That's roughly the width of 2 of your fingernails. It seems like an impossibly tiny distance on the scale of the 240,000 miles that currently separate us. But this small, steady migration has profound implications that will utterly transform Earth over billions of years. The engine behind this lunar escape is a gravitational tug of war between Earth and the Moon, mediated by our planet's oceans. The Moon's gravity pulls on Earth, and it pulls hardest on the world's most flexible feature, the global ocean. This creates a bulge of water on the side of Earth facing the Moon. However, because Earth rotates on its axis so much faster than the Moon orbits us, our planet's spin actually drags this watery bulge ahead of the direct line between Earth and the Moon. This off-center bulge of mass then exerts its own gravitational pull back on the Moon. This constant, slight tug acts like a gentle but incessant accelerator, feeding energy into the Moon's orbit and causing it to spiral outward away from us year after year. But this cosmic transaction comes with a cost. Energy cannot be created or destroyed, only transferred. The energy being given to the Moon's orbit is being stolen from somewhere else, Earth's own rotational energy. This same interaction is acting as a brake on our planet's spin, gradually slowing down the length of our day. Billions of years ago, just after the colossal impact that formed the Moon, an Earth day was only about 5 hours long. The slowing has been immense over deep time, and it continues today, lengthening our day by about 1.7 milliseconds per century. Again, it seems minuscule, but it adds up inexorably over millions and billions of years. So what does this mean for the distant future? The story ends with a fundamental change in the Earth-Moon relationship. The system will continue to evolve until Earth's rotation and the Moon's orbit become synchronized. This means a single day on Earth will last as long as a single month, which itself will be about 47 of our current days. From the surface of this future Earth, the Moon would no longer rise and set. It would hang motionless in the sky, visible only from one hemisphere of the planet. The relentless tidal forces that drive this change will have finally ceased, and the Moon's slow retreat will come to an end. Our planet will be a very different world, with drastically altered tides and a day-night cycle almost unrecognizable to us. This gradual drifting apart is a powerful reminder that even the most seemingly permanent features of our sky are in a state of constant dynamic flux. The celestial clockwork we often take for granted is actually a slow-moving dance of gravity and momentum, one that is patiently reshaping our world and our place in space on a timescale almost too vast for us to comprehend. But if the slow, graceful dance of the Moon feels like a predictable cosmic clock, the true nature of the void it moves through is anything but. This brings us to truth number 5, which might be the most fundamentally bizarre idea we've encountered yet. The absolute perfect emptiness of space is a complete illusion. What we perceive as a silent black vacuum is in reality a seething, bubbling, frenetic sea of energy. Space itself is not empty, it is alive with spontaneous activity, a quantum foam where particles flicker into and out of existence in a relentless, universe-wide dance. This astonishing concept comes from the world of quantum mechanics, which tells us that on the very smallest scales, the universe operates by a completely different set of rules. One of its core principles is the Heisenberg uncertainty principle, which, among other things, places a fundamental limit on how precisely we can know the energy of a system for a given period of time. This isn't a limit of our technology, it's a built-in feature of reality. Because of this uncertainty, empty space can never truly have zero energy. Instead, it's filled with a roiling background of energy fluctuations. Think of it like a vast, calm ocean. From a distance, it looks perfectly flat and still, but if you could shrink down to the size of a single atom, you would see a chaotic, frothing turmoil of waves and bubbles constantly appearing and disappearing. And within that quantum foam, something incredible happens. These energy fluctuations can momentarily congeal into pairs of virtual particles, a particle and its antimatter counterpart. Out of absolutely nothing, a tiny speck of matter and a tiny speck of antimatter spontaneously burst into existence. But here's the catch, they are doomed from the start. According to the laws of physics, they cannot exist for long. Almost instantly, within an unimaginably tiny fraction of a second, the particle and antiparticle find each other and annihilate, returning their borrowed energy back to the vacuum from which they came. This isn't a rare event, it's happening everywhere all the time. Trillions upon trillions of these virtual particle pairs are popping into and out of existence in the space around you, in the space between the stars, and in the space inside your own body right now. The entire universe is a stage for this endless, chaotic production and destruction. You might rightly ask, if we can't see or detect these particles directly, how can we possibly know they are real? The answer is that while the particles themselves are virtual, their effects are very much real and measurable. The most famous demonstration of this is the Casimir effect, a stunning experimental proof that this quantum energy sea is not just theoretical. Imagine two plain, uncharged metal plates placed incredibly close together in a perfect vacuum, parallel to each other. Classical physics would say that nothing should happen between them, it's just empty space. But quantum mechanics tells a different story. In the vastness of space outside the plates, virtual particles of all wavelengths can flicker into being. In the narrow gap between the plates, however, only particles with specific wavelengths that can fit between the plates can appear. This means there are more virtual particles and their associated pressure outside the plates than there are between them. The result, the greater external pressure literally pushes the two plates together, and this is exactly what happens in laboratory experiments. Two plates in a vacuum with no other forces acting on them will gently move toward each other, pulled by the invisible pressure of the quantum vacuum itself. It is a direct physical measurement of nothingness pushing on something. This underlying energy of space, often called zero-point energy because it exists even at absolute zero temperature, is not a small force. The calculated energy density of this quantum vacuum is staggeringly, almost absurdly enormous. In fact, if our theories are correct, there should be so much energy inherent in every tiny volume of empty space that it would have caused the universe to tear itself apart immediately after the Big Bang. The fact that it didn't, and that we instead measure a much smaller value for the energy of empty space, what we call dark energy, is one of the greatest unsolved mysteries in all of physics, often called the cosmological constant problem. It represents a discrepancy between theory and observation of over 100 orders of magnitude, the largest mismatch in the history of science. So the next time you look up at the night sky and see the vast, dark emptiness between the stars, remember that you are not looking at nothing. You are looking at the most active, energetic, and dynamic thing imaginable. You are witnessing the foundational canvas of reality itself, a quantum stage where existence is perpetually rehearsing its own creation and destruction. The void is not void at all, it is the source of everything. But if the quantum foam reveals a hidden turbulence within the void, our next truth points to a profound and universal stillness. Truth number 6, the entire universe has a temperature. No matter where you go in the cosmos, if you could place a thermometer in the deepest, darkest, most empty patch of space imaginable, far from any star or galaxy, it would not read absolute zero. Instead, it would register a faint but definitive chill, 2.7 degrees above absolute zero, or negative 270 degrees Celsius. This is not a coldness born of absence, it is the fading warmth of creation itself, the afterglow of the Big Bang. We call it the cosmic microwave background radiation, and it is the oldest light in the universe, a snapshot of its infancy that fills every cubic centimeter of space. To understand what we're hearing in this cosmic whisper, we need to rewind the clock all the way back to the universe's earliest moments. For about the first 380,000 years after the Big Bang, the cosmos was an entirely different place. It wasn't empty and dark, it was an incredibly hot, dense, and opaque fog of plasma. The universe was so intensely energetic that atoms couldn't even form. Protons and electrons were constantly zipping around, bouncing off photons, particles of light in a chaotic, scorching soup. Light was trapped, unable to travel in a straight line, constantly scattering off the free-flying electrons. It was a brilliant, blinding white-hot glow, but you wouldn't have been able to see anything if you were there because there was no clear space for light to travel through. Then, in a pivotal moment known as recombination, the universe expanded and cooled just enough for a monumental change to occur. The energy level dropped below a critical threshold, allowing protons to finally capture those free electrons and form the first stable hydrogen atoms. Suddenly, the fog lifted. With most of the electrons now locked into atoms, the photons, which had been trapped for millennia, were set free. For the first time, light could stream across the universe unimpeded. That first flash of liberated light is what we detect today as the cosmic microwave background. It is the echo of that moment of clarity, stretched and faded by 14 billion years of cosmic expansion. And what an incredible journey that light has had. The universe has expanded by a factor of over 1,000 since that moment. This incredible stretching has fundamentally transformed the light itself. Think of the light wave being drawn out like an ink mark on a stretching rubber band. When it was first emitted, that light was incredibly energetic, a brilliant visible light, even shining in the ultraviolet range. But over billions of years, the expansion of space itself has stretched its wavelength all the way from the visible spectrum down into the microwave part of the spectrum. This is why we call it the cosmic microwave background. Its energy has been drastically reduced, cooling from thousands of degrees to just a few degrees above absolute zero. We are essentially listening to the universe's baby picture that has been faded and redshifted into a faint, cold whisper. Detecting this whisper was one of the greatest scientific achievements of the 20th century. In the 1960s, two astronomers at Bell Labs, Arno Penzias and Robert Wilson, were working with a highly sensitive microwave antenna. No matter where they pointed it, they kept finding a persistent, annoying static hiss that filled the entire sky equally. They scrubbed the antenna, checked for interference, and even evicted a pair of pigeons nesting in the horn, cleaning out what they referred to as a white dielectric material, but the noise remained. This pervasive signal, which they couldn't explain, was actually the signature of the birth of the universe itself. They had accidentally discovered the cosmic microwave background, a finding that earned them the Nobel Prize and provided the smoking gun evidence that the Big Bang model was correct. But the story doesn't end there. Modern satellites like the Cosmic Background Explorer and the Planck spacecraft have mapped this background radiation with exquisite precision. And what they found is even more fascinating. The temperature is not perfectly uniform across the sky. It is almost perfectly even, varying by only tiny fractions of a degree. These minute fluctuations, these tiny hotspots and cold spots in the microwave sky, are of monumental importance. They represent the seeds of all future structure in the universe. They are the imprints of tiny density variations in the early plasma, slightly denser regions where gravity had a little more to work with. Over billions of years, gravity amplified these tiny imperfections, pulling more and more matter into them. The slightly denser spots became the first galaxies, then clusters of galaxies, and the vast cosmic web we see today. Every galaxy, every star, every planet, and every one of us originated from a tiny quantum fluctuation imprinted on this ancient light. So when you see the static on an old television set, about 1% of that snow is actually the cosmic microwave background radiation, the residual static from the Big Bang. It is a tangible connection to the very beginning of everything, a fossilized bubble of light that has been traveling for nearly 14 billion years to reach us, carrying with it the secrets of the universe's fiery birth and the blueprint for everything that was to come. And if the faint, cold glow of the Big Bang makes the universe feel ancient and settled, our next truth suggests its story might be far from over, potentially even duplicated in a reality that is a perfect mirror of our own. Truth number 7, there might be an entire mirror universe, a perfect reflection of our own where time runs backward and everything is made of antimatter. This isn't just wild speculation, it's a serious physics theory born from one of the greatest unsolved mysteries in science, the baffling absence of antimatter. To understand why this is such a profound puzzle, we need to start with one of the most well-established facts in particle physics. Matter and antimatter are twins. For every type of matter particle that exists, there is a corresponding antimatter particle with the same mass but the opposite electric charge. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy, returning to the void from which they came. And according to everything we know about the laws of physics, the Big Bang should have created matter and antimatter in absolutely equal amounts. One proton for every antiproton, one electron for every positron, and so on. In the frenetic energy of the early universe, pairs of particles and antiparticles should have been bursting into existence and then almost immediately finding each other and annihilating. If that had happened perfectly, the final result of the Big Bang would have been a universe containing nothing but energy, a vast, expanding sea of light with no atoms, no stars, no planets, and certainly no us. But clearly, that's not what happened. Our universe is filled with galaxies, stars, and planets made of matter. Somehow, against all odds, a tiny, tiny imbalance occurred. For every 1 billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. That 1 in a billion excess is all we are. Everything we see in the cosmos is the leftover ash from that near-perfect annihilation. The monumental question is, why? What fundamental law of physics allowed that 1 in a billion advantage for matter, breaking the perfect symmetry and allowing our universe to exist? Physicists have searched for decades for any slight difference in the behavior of particles and antiparticles that could explain this bias, a phenomenon known as CP violation. And while we have found a few very small examples of this asymmetry, they are nowhere near powerful enough to account for the overwhelming dominance of matter we see today. The observed violations are like finding a single dropped coin when we need to account for a missing fortune. This leaves a gaping hole in our understanding, a mystery that points to either a fundamental flaw in our models or a cosmological clue of staggering proportions. One of the most elegant and mind-bending solutions to this puzzle is the idea of a CPT symmetric universe. CPT symmetry is considered a sacred cornerstone of modern physics. It states that if you take a particle and simultaneously perform three operations, charge conjugation C, turning it into its antiparticle parity inversion P, flipping it as if in a mirror, and time reversal T, running its clock backward, the laws of physics should remain exactly the same. The particle should behave identically to its original self. No experiment has ever violated CPT symmetry. It seems to be an absolute rule, but if it's an absolute rule and our universe began with a net amount of matter, then somehow that symmetry must be preserved on a cosmic scale. This is where the theory of a mirror universe comes in. Some physicists, like Nobel laureate Sheldon Glashow, have proposed a breathtaking possibility that the Big Bang did not create one universe but two. Our universe with its matter and forward arrow of time, and a second, anti-universe that extends backward in time from the Big Bang and is made predominantly of antimatter. In this view, the two universes are perfect CPT reflections of each other. Our universe moving forward in time with matter is the mirror image of a universe moving backward in time with antimatter. Together, they form a perfectly symmetric whole that satisfies the fundamental laws of physics, explaining the missing antimatter not as a violation but as a separation. The antimatter isn't gone, it's just in the other universe. Trying to picture this is a true test of our imagination. From the moment of the Big Bang, two universes would have unfurled in opposite temporal directions. In our sister universe, time would flow backward from our perspective. Their Big Bang is our distant future, and our Big Bang is their distant future. A citizen of that universe would not experience time in reverse. From their subjective viewpoint, their consciousness would flow forward just as ours does, and they would perceive our universe as the one moving backward. They would be made of antimatter, but they would call it matter, and they would look out at their cosmos of antimatter galaxies and stars and see it as perfectly normal. They would be asking the exact same question we are. Where did all the matter go? This idea transforms the antimatter problem from a local mystery into a cosmic feature. We don't see antimatter because it predominantly exists in a parallel reality that is causally disconnected from our own, a mirror image fleeing from us in the opposite direction of time. While this remains a highly theoretical concept, it is a powerful example of how the most perplexing gaps in our knowledge can lead to the most revolutionary ideas, suggesting that the true nature of reality might be far grander and more interconnected than we ever dreamed. And yet, if the idea of a mirror universe feels like it's stretching the very fabric of reality, our next truth takes us to a place where the fabric of reality itself is torn apart. Truth number 8 reveals one of the most beautiful and paradoxical ideas in all of physics. Black holes aren't actually black, they glow, they emit radiation. And in a process that takes longer than the current age of the universe, they can even evaporate completely, vanishing in a final, silent puff of energy. This stunning discovery, made by Stephen Hawking, completely upends the classical view of these cosmic monsters, proving that even from the most absolute prison in the universe, something can and does escape. The classical picture of a black hole, born from Einstein's theory of general relativity, is terrifying in its finality. It's a region of space where gravity is so intense that the escape velocity exceeds the speed of light. The boundary around it, the point of no return, is called the event horizon. Cross that invisible line, and not even light has enough energy to fight its way back out. To an outside observer, the black hole is the ultimate endpoint, a one-way street where things go in but nothing, not a single particle of information ever comes out. It is the universe's most perfect vacuum cleaner, and it appeared to be eternally black, a permanent and growing scar on the cosmos. But this picture creates a profound problem when you introduce the other great pillar of modern physics, quantum mechanics. Quantum theory tells us that information cannot be truly destroyed. the specific configuration of particles that makes up an object. Say, a book might be scrambled, but in principle, that information should always be recoverable. If you burn the book, you could, with a godlike understanding of physics, trace the smoke and ashes back to reconstruct every word. But a black hole seemed to violate this fundamental principle. Throw the book into a black hole, and according to classical theory, it's gone forever. The information is irretrievably lost behind the event horizon. This contradiction is known as the black hole information paradox, and it suggested that our two most successful theories of reality were fundamentally incompatible. Stephen Hawking set out to resolve this paradox by applying quantum rules to the edge of a black hole, and what he found was astonishing. He realized that the event horizon is not a calm, placid boundary. It is a place of violent quantum activity where the weird rules of the subatomic world create a loophole for escape. Remember the quantum foam we discussed earlier, that seething sea of virtual particles flickering in and out of existence everywhere in space. This phenomenon is happening right at the edge of the event horizon too. Normally, these particle-antiparticle pairs pop into existence and annihilate each other so quickly we can't detect them. But at the event horizon, something drastic can happen. Imagine a pair of virtual particles spontaneously appearing just outside the black hole's point of no return. In a fantastically rare but possible scenario, one particle of the pair might appear just on the outside of the horizon, while its partner appears just on the inside. The particle outside, if it has enough energy, can escape into the universe, becoming a real particle. But its unlucky partner, now trapped inside the horizon, is doomed to fall into the black hole's singularity. From the perspective of energy conservation, this process seems like theft. The universe has gained a real particle with positive energy, which must be balanced by a loss somewhere else. That loss is taken from the black hole itself. The incoming particle has negative energy relative to the outside universe. When this negative energy particle falls into the black hole, it effectively reduces the black hole's total mass and energy. The black hole has paid a toll for the particle that escaped. To an observer watching from a safe distance, it looks as if the black hole has just emitted a particle of radiation. This is Hawking radiation. It's not coming from within the black hole. Nothing breaks out from behind the event horizon. Instead, it is generated right at the precipice, a quantum effect that allows energy to slowly leak away from the gravitational behemoth. The properties of this radiation are what make it so strange. Hawking radiation is thermal radiation. It has a spectrum identical to that of a glowing hot object, like the filament in a light bulb, but incredibly cold. The temperature of a black hole is inversely proportional to its mass. A typical stellar mass black hole, with several times the mass of our Sun, would have a Hawking temperature of just a tiny fraction of a degree above absolute zero. This means it actually absorbs more energy from the cosmic microwave background radiation than it emits, causing it to grow very, very slowly. But as the universe expands and cools, that background radiation will eventually fade to near nothing. Then the black hole's slow evaporation will begin in earnest, and this is where the true cosmic timescale comes into play. For a black hole with the mass of our Sun, the process of evaporation would take an almost incomprehensible 10 to the 67 years, a 1 followed by 67 zeros. That is far, far longer than the current age of the universe, but for smaller black holes the process is much faster. A black hole with the mass of a small asteroid would be emitting Hawking radiation as high-energy gamma rays and would evaporate in a time frame comparable to the age of the universe. As a black hole loses mass, its temperature increases. The less massive it becomes, the hotter it gets, and the faster it radiates energy away. The final moments of a black hole's life would be a runaway explosion, a silent, invisible flash of high-energy radiation as the last of its mass converts into particles and flashes out across the cosmos. This incredible process solves the information paradox in the most elegant way possible. the information that fell into the black hole isn't destroyed. It's not lost behind the horizon forever. It is encoded in some incredibly complex and scrambled way into the Hawking radiation itself. As the black hole radiates, it slowly reveals that information back to the universe. The entire life cycle of a black hole, from its formation to its eventual complete evaporation, becomes a transformative process, not a destructive one. It takes matter and energy, encodes it onto its event horizon, and then, over eons, slowly and faithfully returns it to the cosmos as radiation. The black hole is not an eternal tomb. It is a cosmic recycler operating on a timescale that dwarfs all of human history. This brings us to one of the most counterintuitive and mind-stretching truths of all. The universe is expanding, and for the most distant galaxies, that expansion is happening at a rate that far exceeds the speed of light. Now, if your first thought is that this sounds impossible, a direct violation of Einstein's cosmic speed limit, you're in good company. It feels like a fundamental rule is being broken. But the key to understanding this apparent paradox lies in a crucial distinction, one that separates the motion of objects through space from the expansion of space itself. One is governed by relativity, the other is the stage upon which relativity performs. Einstein's famous rule that nothing can travel through space faster than the speed of light remains one of the most ironclad laws in physics. It dictates the maximum velocity for any matter, information, or energy making a journey across the cosmos. A spaceship, a beam of light, a radio signal, all are bound by this limit. They are players moving on the cosmic stage, but the stage itself, the very fabric of space-time, operates under a completely different set of rules. There is no known speed limit for the expansion of space. Space can stretch, and the distance between 2 points can grow at any rate the universe sees fit. This isn't an object moving, it's the canvas itself getting larger, carrying the galaxies painted upon it along for the ride. A simple analogy can help make sense of this strange idea. Imagine the universe as a loaf of raisin bread dough rising in a vast oven. Each raisin represents a galaxy. As the dough expands, every raisin moves away from every other raisin. Now focus on 2 raisins that are very close together. The dough between them doesn't have to stretch very far to increase their separation by, say, a centimeter. But now consider 2 raisins on opposite ends of the loaf. The dough between them is much greater. For the same overall rate of expansion, the actual speed at which those 2 distant raisins move apart is much, much faster because there's just so much more expanding dough between them. If the loaf is big enough and the expansion fast enough, those 2 raisins on opposite ends could indeed be moving apart faster than any single raisin could possibly crawl through the dough. The raisins aren't propelling themselves, they are simply being carried by the expanding medium they are embedded in. This is precisely what is happening on a cosmic scale. Galaxies are not rocketing away from us through space like bullets from a gun. Rather, the space between our galaxy and theirs is continuously stretching, increasing the distance. The farther away a galaxy is, the more expanding space there is between us, and therefore the faster it appears to be receding. At a certain critical distance, known as the Hubble radius, that recession velocity mathematically reaches and then surpasses the speed of light. This means the light those ultra-distant galaxies are emitting right now is traveling toward us at light speed, but the space it has to cross is stretching so rapidly that the photon is actually losing ground. It's like a swimmer trying to cross a river that is widening faster than they can paddle. That light may never reach us. Those galaxies have effectively passed beyond our cosmic event horizon, forever lost to our future view. This reality has a profound and somewhat lonely consequence. Due to this accelerating expansion driven by dark energy, there is a growing sphere of the universe that is now permanently beyond our reach. We can still see the light from incredibly distant galaxies that left billions of years ago, a fossil record of the ancient universe. but we will never see what those galaxies look like today, and any civilizations out there will never see the light from our sun as it is now. We are forever separated by an ever-widening gulf that not even light can bridge. The observable universe, the portion we can ever hope to see or interact with, has a finite size and is actually getting smaller in terms of the overall percentage of the total universe we can access. So, while nothing can ever win a race through space against a beam of light, space itself has no such restrictions. It can outpace light effortlessly, carrying the most distant islands of stars away from us on a current we can never hope to sail against, forever redefining the boundaries of the knowable cosmos. This profound connection between our bodies and the cosmos brings us to truth number 10, a poetic and scientifically robust reality that we are all quite literally made of stardust. Every atom in our bodies that is heavier than hydrogen and helium, the carbon in our cells, the oxygen we breathe, the iron in our blood, the calcium in our bones, was forged in the nuclear furnaces of long-dead stars and scattered across the galaxy in violent, brilliant stellar explosions. You are not just living in the universe is living in you, a walking, talking collection of ancient cosmic artifacts. To understand how this cosmic alchemy works, we have to journey back to the very beginning. In the first few minutes after the Big Bang, the universe was a seething, expanding cauldron of energy cooling into matter. During this period, known as Big Bang nucleosynthesis, the only elements that could form were the very lightest, primarily hydrogen, about 75% of the normal matter by mass, and helium, making up nearly the other 25%, with just trace amounts of lithium. For hundreds of millions of years, the universe was a vast, simple soup of these primitive elements. There was no carbon, no oxygen, no nitrogen, none of the complex ingredients necessary for planets, oceans, or life. The cosmos was pristine but lifeless. The transformation began when gravity started to pull together enormous clouds of this primordial hydrogen and helium. As these clouds collapsed under their own weight, the pressure and temperature at their cores became so immense that they ignited the process of nuclear fusion, and the first stars were born. Inside these stellar forges, the universe's chemistry set was finally turned on. At temperatures of millions of degrees, hydrogen nuclei single protons slammed together to form helium, releasing the tremendous energy that makes stars shine. This is the same process that powers our sun today. For most of a star's life, this hydrogen fusion is its primary engine, but for a star much more massive than our sun, the story doesn't end there. Once the hydrogen fuel in its core is exhausted, the core begins to contract under gravity's relentless pull, heating up even further. This rise in temperature opens the door to the next chapter of fusion. When the core reaches about 100 million degrees, helium nuclei can begin to fuse together. Two helium nuclei form unstable beryllium, but if a third helium nucleus collides in just the right way before the beryllium falls apart, it creates a stable nucleus of carbon. This crucial three-step process, known as the triple alpha process, is how the universe built its first atoms of carbon, the fundamental backbone of all known life. The star's life becomes a layered, desperate struggle against gravity. With each fuel source exhausted, the core contracts and heats up again, triggering the fusion of ever heavier elements. Carbon can fuse into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each step releases less energy than the one before it and happens more quickly. The fusion of elements up to iron actually produces energy, which provides the outward pressure that temporarily holds the star up against its own immense gravity. But iron is the end of the line. Fusing iron into heavier elements does not release energy, it consumes it. The star's core, now an iron ingot, has lost its main source of pressure. With no outward force to counter gravity, the core collapses catastrophically in less than a second. This collapse triggers one of the most violent events in the universe, a core collapse supernova. The outer layers of the star, no longer supported, come crashing down at incredible speed onto the inert iron core. The impact is so tremendous that it creates a shockwave of unimaginable force that blasts the entire star apart, outshining an entire galaxy of stars for a brief, spectacular moment. In the ferocious energy of this explosion, two incredible things happen. First, the flood of neutrons in the dense environment allows atoms to rapidly capture them, creating elements heavier than iron like gold, silver, platinum, and uranium through a process called rapid neutron capture, or the R process. Second, and just as importantly, the entire enriched contents of the star, the carbon, oxygen, nitrogen, and all the newly forged heavy elements, are violently hurled out into the surrounding interstellar space at nearly 1/10 the speed of light. This ejected stellar material, this cosmic fertilizer, mixes with the surrounding clouds of hydrogen and gas. Over millions of years, this enriched cloud, seeded with the elements for life, will collapse under gravity to form a new generation of stars. But this time, because the cloud contains heavier elements, it can also form rocky planets, asteroids, and comets. Our own solar system formed from such a cloud about 4.6 billion years ago, a cloud that had been enriched by the death throes of several previous generations of massive stars. The iron in your blood that carries oxygen to your cells was likely forged in the core of a star that lived and died billions of years before our sun was even a glimmer in a nebula. The iodine essential for your thyroid function was almost certainly created in the R process of a supernova. The gold in a wedding ring or the uranium in a power plant are relics of stellar cataclysms of unbelievable power. So when you look up at the night sky, you are not just a separate observer looking at distant, unrelated points of light. You are the universe looking back at itself. The calcium that forms the structure of your bones was once part of a star that died so that you could one day exist. The oxygen you just inhaled with your last breath was manufactured in a stellar furnace and then scattered across light years of space, eventually finding its way into our atmosphere and into your lungs. We are not simply inhabitants of the cosmos, we are a physical part of its grand, dynamic cycle of birth, death, and rebirth. Our very existence is the most beautiful and intimate proof that the universe has a history, and that we are connected to the stars not by metaphor, but by the very atoms that define us. Yet for all the profound connection we share with the cosmos, our universe might be just one page in an infinite library of realities. Truth number 11 presents perhaps the most expansive idea in all of science. Our entire cosmos, with all its hundreds of billions of galaxies and its specific set of physical laws, might be just one single bubble in a vast, frothing ocean of universes, a multiverse. This isn't merely a science fiction trope, it's a serious theoretical consequence emerging from our most advanced cosmological and physical models, suggesting that everything we know could be a tiny, local exception in a reality of infinite variety. The most compelling evidence for this staggering idea comes from a theory designed to solve some of the biggest puzzles about our own universe: cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the fabric of space-time itself underwent a period of hyper-fast, exponential expansion, inflating from a subatomic speck to something macroscopic in an unimaginably short time. This explosive growth neatly explains why our universe is so large, so uniform, and so flat. But here's where the multiverse enters the picture. According to the prevailing models, this inflation didn't just start and stop everywhere at once. Instead, it's likely eternal. Once inflation begins, quantum fluctuations can prevent it from stopping everywhere simultaneously. Think of it like a pot of water beginning to boil. Our universe is like a single bubble that formed in that boiling water and then stopped expanding, allowing it to cool and form galaxies and stars. But the boiling process itself, the inflationary energy field, never stops. Outside our bubble, the frantic boiling continues and new bubbles are constantly nucleating. each one a new universe with its own Big Bang, inflating into its own separate space-time realm. This process is eternal, creating an endless chain of bubble universes within an ever-expanding inflationary background. These universes are not connected by any common space or time. They are truly separate, isolated realities, forever beyond our reach or observation. But the real mind-bending consequence of this is what happens inside each of these bubbles. When a new universe forms and its inflation ends, the immense energy that drove the expansion has to go somewhere. It is released, flooding that new universe and condensing into particles and radiation. However, the way this energy condenses can vary. This is where the laws of physics themselves might be set. The fundamental constants, the strength of gravity, the mass of an electron, the strength of the nuclear forces, might not be universal constants at all. They could be more like local variables frozen into random values during the formation of each bubble universe. In this eternal inflation scenario, every possible combination of physical constants and laws should arise in some universe somewhere in the multiverse. This provides a potential and deeply controversial solution to one of the most perplexing questions in physics. Why is our universe so perfectly tuned for life? If the strength of the nuclear force were even slightly weaker, protons and neutrons wouldn't bind together and no complex atoms could form. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars like our Sun. If the cosmological constant were a bit larger, the universe would have ripped itself apart before galaxies could form. If it were smaller, it would have collapsed back in on itself long ago. The list of these cosmic coincidences is long and puzzling. The multiverse idea offers an answer. If there are an infinite number of universes, each with random physical laws, then it's no surprise that we find ourselves in one of the rare habitable ones. We are a product of an unimaginable cosmic lottery, and we can only exist in a universe that allows for our existence. This is known as the anthropic principle. Another path to the multiverse comes from string theory, an ambitious attempt to unify all forces and particles into a single theoretical framework. String theory suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. The way a string vibrates determines whether it manifests as an electron, a photon, or a quark. But for the math of string theory to work, it requires more than the 3 spatial dimensions we experience. It requires 10 or 11 dimensions, so where are these extra dimensions? The theory proposes they are curled up or compactified into shapes so small we cannot perceive them. And the specific way these dimensions are curled up determines the laws of physics that emerge in that universe, the values of constants and the number of particle types. Crucially, string theory allows for a colossal number of possible ways these dimensions can curl up, perhaps 10 to the 500 different ways. Each possibility corresponds to a universe with a completely different set of physical laws. This is known as the string theory landscape, and when combined with the eternal inflation model, it suggests that each bubble universe in the multiverse could have its own unique compactification of these extra dimensions, and therefore its own unique physics. In this view, the multiverse is not just vast, it is maximally diverse, containing universes where gravity is repulsive, where time runs in multiple directions, or where the very concept of matter is unrecognizable to us. Of course, the multiverse remains a deeply philosophical and contentious idea, because these other universes are, by definition, causally disconnected from our own. We can never observe them directly or communicate with them. This leads some critics to argue that it is not true science, as it makes no testable predictions. Proponents counter that the theory of inflation, which does make testable predictions for our own universe, naturally leads to the multiverse as a consequence. They argue that to ignore this implication would be unscientific. Furthermore, some theories suggest that if 2 bubble universes were to ever collide, It might leave a detectable imprint on the cosmic microwave background, a faint bruise on the sky that could serve as indirect evidence. While such a signature has yet to be found, the search continues. Whether a proven reality or the ultimate untestable hypothesis, the multiverse concept fundamentally reconfigures our place in existence. It suggests that our entire cosmic history, from the Big Bang to the formation of life, might be just one ordinary story in an infinite anthology of realities. The laws we hold as fundamental and universal might be nothing more than provincial bylaws, relevant only within our own isolated cosmic bubble. It is a thought that is simultaneously humbling and exhilarating, revealing a reality whose true scale and diversity may forever lie beyond the limits of human observation, but not beyond the reach of our imagination. Yet for all the grandeur of cosmic structures and parallel realities, some of the universe's most shocking truths are found in the smallest, most fundamental behaviors of matter and energy. Truth number 12 takes us from the vastness of the multiverse to the perplexing quantum realm, where the very act of observation fundamentally alters reality. It reveals that light, and in fact all matter, possesses a bizarre dual nature. It can behave as both a particle and a wave, and which face it shows depends entirely on whether we are watching. This isn't a limitation of our instruments, it's a core feature of the universe, demonstrated by one of the most famous and confounding experiments in all of science, the double-slit experiment. To understand why this is so revolutionary, we first need to appreciate the classical view. For centuries, scientists were divided. Isaac Newton championed the idea that light was a stream of tiny particles or corpuscles. This could explain why light traveled in straight lines and cast sharp shadows. Others, like Christian Huygens, argued that light was a wave, similar to sound or ripples on a pond. This wave theory elegantly explained how light could bend around corners, a phenomenon called diffraction, and how it could interfere with itself, creating patterns of light and dark. For a long time, the wave model seemed to win out, especially after James Clerk Maxwell's work in the 19th century showed that light was an electromagnetic wave. The definitive proof for light's wave nature came from Thomas Young's double-slit experiment in the early 1800s. The setup is beautifully simple. You have a source of light, a barrier with two very thin parallel slits cut into it, and a screen behind the barrier to capture the result. If light were simply made of particles, as Newton thought, you would expect to see two bright bands on the screen directly behind the two slits where the particles had shot through like bullets. But that's not what happens. Instead, the screen shows a series of multiple, alternating bright and dark bands, known as an interference pattern. This is the unmistakable signature of a wave. Here's why: as a wave of light approaches the barrier, it passes through both slits simultaneously. On the far side, these two new waves spread out and overlap with each other. Where the peaks of the two waves meet, they combine to create a brighter peak constructive interference, creating a bright band. Where a peak from one wave meets a trough from the other, they cancel each other out, completely destructive interference, creating a dark band. This result seemed to settle the debate conclusively. Light was a wave, but the story was far from over. The 20th century brought the birth of quantum mechanics, and with it a shocking twist. Scientists discovered that light could also behave like a particle, a packet of energy called a photon. This particle-like nature was revealed in the photoelectric effect, where light shining on a metal surface could knock electrons loose, but only if the light's color, its frequency, was high enough regardless of its intensity. Albert Einstein won his Nobel Prize for explaining this, showing that light energy was delivered in discrete particle-like packets. So which was it? Was light a wave or a particle? The answer, defying all common sense, was both. The true weirdness of this duality was revealed when scientists decided to perform the double-slit experiment, not with a broad beam of light, but one photon at a time. They used an extremely dim light source, ensuring that only a single photon was traveling through the apparatus at any given moment. Common sense would dictate that a single particle, with nothing to interfere with, should have no choice but to go through one slit or the other and land on the screen as a single dot directly behind that slit. And indeed, when the scientists looked at the screen after firing many photons one by one, each one appeared as a tiny, discrete point of impact, just like a particle. But then they let the experiment run. As thousands upon thousands of these individual photons were fired and their landing positions recorded, an impossible pattern slowly emerged on the screen. It wasn't two clumps of dots, it was the full, elaborate interference pattern of bright and dark bands. This was a staggering result. Each individual photon had to be passing through both slits at the same time and interfering with itself to create this pattern. The single photon was behaving as if it were a wave spread out across space, traveling through both pathways simultaneously, and only deciding to collapse into a single, particle-like point upon hitting the screen. This was bizarre enough, but the experiment held one more profound twist: the role of the observer. Scientists wondered what would happen if they tried to catch the photon in the act, to determine which of the two slits it actually went through. They placed a detector at one of the slits to register the passage of a particle. The moment they did this, the incredible interference pattern vanished. The screen now showed only two bright bands, the simple pattern you would expect from particles. The mere act of measuring, of observing which path the photon took, forced it to behave like a particle that went through one slit or the other. Its wave-like behavior and its ability to be in two places at once collapsed under the gaze of measurement. This result isn't unique to light. The same experiment has been done with electrons, atoms, and even large molecules, all with the same result. All matter possesses this wave-particle duality. Everything in the universe has an associated wave nature, a wavelength determined by its momentum. For everyday objects like a baseball, this wavelength is immeasurably tiny, but for a tiny electron, it's significant. This means that, according to the math of quantum mechanics, until it is observed or interacts with something, that electron isn't in a specific location. It exists in a smear of probability, a cloud of potential locations described by a wave function. It is only when we look, when we measure, that this probability cloud collapses into a definite reality. The implications of this are earth-shattering for our understanding of reality. It suggests that at its most fundamental level, the universe does not exist in a definite, concrete state. Instead, it exists as a tapestry of possibilities, a realm of potentialities. The act of observation isn't a passive process of seeing what's already there. It is an active process that participates in bringing a specific reality into being. This doesn't mean consciousness creates reality in a mystical sense, but rather that any interaction that gains information, a photon hitting a detector, an atom bumping into another atom, can cause this collapse. Reality, it seems, is not what we thought it was. It is fuzzy, probabilistic, and deeply interconnected, waiting to be sharpened into the world we experience through the very process of interaction itself. And while the quantum world challenges our notions of a fixed reality, our next truth brings us back to a more sensory and oddly familiar cosmic experience. Truth number 13. The vast cloud of gas and dust at the center of our Milky Way galaxy smells distinctly like raspberries and rum. This isn't a poetic metaphor or the premise of a science fiction novel. It's a factual statement based on the concrete detection of specific organic molecules floating in the interstellar void, a discovery that profoundly changes our understanding of the chemical richness of space. The scene of this aromatic discovery is a massive molecular cloud known as Sagittarius B2. Located near the supermassive black hole at the very heart of our galaxy, about 26,000 light-years from Earth, this cloud is a stellar nursery of epic proportions. It's one of the largest clouds of its kind in the Milky Way, a titanic structure of gas and dust so dense that it's the site of intense star formation. But for chemists and astrobiologists, its true treasure isn't the stars being born, but the incredibly complex soup of chemicals swirling within it. For decades, radio astronomers have been pointing powerful telescopes like the ARAM 30-meter telescope in Spain toward Sagittarius B2, not to see it with light, but to listen to it with radio waves. Every molecule in space, as it tumbles and rotates, emits a unique fingerprint of radiation at specific radio frequencies. It's like each compound has its own musical note that it sings. By carefully tuning their receivers across the radio spectrum, astronomers can identify these molecules by their precise spectral signatures, building a chemical inventory of the cosmos from light years away. And the list of molecules found in Sagittarius B2 is astonishing. They've detected everything from simple carbon compounds like formaldehyde and hydrogen cyanide to more complex organic molecules like vinyl alcohol and glycolaldehyde, a simple sugar. But the molecule that truly captured the public's imagination is ethyl formate. This compound is an ester, a type of molecule frequently responsible for the flavors and aromas of fruits. When astronomers analyzed the spectral data from Sagittarius B2, they found the unmistakable signal of ethyl formate. Now, if you were to open a bottle of pure ethyl formate in a laboratory on Earth, you would be greeted by a powerful scent that is a nearly perfect blend of ripe raspberries and the rich, warm aroma of rum. This means that the same chemical compound that gives raspberries their delicious smell and contributes to the distinctive bouquet of rum is floating in immense quantities in a giant cloud near the center of our galaxy. Of course, it's crucial to understand that you wouldn't actually want to take a deep breath if you could somehow visit Sagittarius B2. For one, it's a vacuum, there's no air to breathe. The molecules are so sparse that your nose would have to sample an impossibly large volume of space to get a whiff. And more importantly, the cloud is a mix of countless chemicals. Alongside the pleasant-smelling ethyl formate are vast quantities of far less appealing substances, including hydrogen sulfide, which smells like rotten eggs, and ammonia, which has a pungent, acrid odor. The overall scent would likely be a confusing and overwhelmingly unpleasant cocktail, with the sweet notes of rum and raspberries utterly drowned out by the stench of cosmic rot and poison. Yet the presence of ethyl formate and other complex organic molecules is far more significant than a fun astronomical factoid. It is a powerful clue in one of humanity's greatest quests to understand the origins of life. The detection of these molecules tells us that the fundamental building blocks of biology, the precursors to amino acids, sugars, and the components of DNA are not unique to Earth. They are being forged in abundance in the icy depths of interstellar space, on the surfaces of dust grains within clouds like Sagittarius B2. Through processes catalyzed by starlight and cosmic rays, simple atoms are linking together to form these more complex structures. Eventually, when a new solar system forms from a cloud like this, all of these pre-made organic ingredients are incorporated into the mix. They become part of the raw material of protoplanetary disks, seeding fledgling planets with the chemical potential for life. The sugar glycolaldehyde found in space, for example, can react with other compounds to form ribose, a key sugar in RNA. The discovery that the galaxy's center smells of rum and raspberries is therefore a delightful shorthand for a profound truth. The universe is not a barren, empty place. It is a vast chemical factory already preloaded with the essential ingredients for life long before planets even form. We are not just made of stardust, we may very well be seasoned with the flavors of the cosmos. But if the universe has a smell, perhaps its greatest trick is convincing us that the flow of time is real. This brings us to truth number 14, a concept so fundamental it threatens to unravel our entire experience of reality. Time itself may not exist. Not as a fundamental force, not as a universal river flowing from past to future, but as an illusion, an emergent property that bubbles up from a more basic, timeless reality beneath. This isn't philosophical musing. It's a serious conclusion being drawn from our most advanced attempts to unite the two pillars of modern physics, quantum mechanics and general relativity. We experience time as an unstoppable, one-way progression. The past feels fixed, a memory. The present is the immediate moment of experience. The future is unknown, a realm of possibility. This arrow of time feels as real and concrete as the ground beneath our feet. But when physicists write down the equations that govern the universe, a strange thing happens. The fundamental laws of physics, from Newton's mechanics to Einstein's relativity to quantum electrodynamics, are almost entirely time-symmetric. They work perfectly well whether time is moving forward or backward. There is nothing in the core math that picks out a preferred direction for time's flow. The stark difference between our experience and the laws of physics is perhaps best illustrated by the work of a scientist named Emmy Noether. In the early 20th century, she discovered a profound connection between symmetries in nature and conservation laws. One of her theorems shows that the fact that the laws of physics don't change over time, their symmetry in time, is directly linked to the conservation of energy. The equations don't care about now, they just are. The flow we feel so acutely is absent from the bedrock mathematics of reality. So where does the arrow of time come from? The most compelling answer points to a concept called entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This is why an ice cube melts in a warm room but never spontaneously reforms, why a shattered cup doesn't leap off the floor and reassemble itself. The universe moves from order to disorder, and this increase in entropy gives us a powerful, experiential arrow of time. But this only pushes the mystery back one step. Why was the entropy of the early universe so incredibly low? Why did it start in such a highly ordered state, providing the necessary gradient for time to appear to flow for billions of years? This remains one of cosmology's deepest questions. The plot thickens significantly when we look at the cutting edge of theoretical physics, particularly in the quest for a theory of quantum gravity, a framework that can describe the intense gravity of black holes and the singularity of the Big Bang. Two of the most prominent approaches, string theory and loop quantum gravity, both seem to suggest in their own ways that time is not a fundamental ingredient. In these theories, the most basic description of reality is a timeless mathematical structure. Time, as we know it, doesn't appear in the core equations. Instead, it is thought to be an emergent property, a macroscopic illusion that arises from the relationships between other, more fundamental things. Think of it like the concept of temperature. If you look at a single molecule of air flying around a room, it doesn't have a temperature. Temperature is a property that only makes sense when you have a vast collection of molecules. It emerges from their collective statistical motion. In a similar way, some physicists propose that time emerges from the complex interactions of a vast number of fundamental quantum entities. Our perception of duration and change could be a useful approximation, a story our brains tell us to make sense of this underlying, timeless network of correlations. This radical idea leads to a fascinating reinterpretation of the universe called the block universe theory. In this view, inspired by Einstein's relativity, past, present, and future are all equally real. They all exist laid out together in a four-dimensional block of space-time. The feeling that the now is special and that the future is becoming the present is just a feature of our consciousness. In the block universe, your birth, your life, and your death all exist eternally within the static geometry of space-time. You are a world line, a path through the block. The sense of flow is a psychological illusion, a trick of the mind as it moves along this fixed path. the implications of a timeless universe are staggering. It challenges the very notion of free will, of cause and effect as we understand it. If the future is already out there, just as fixed as the past, then what does it mean to make a choice? Furthermore, it forces us to reconsider what physics is even supposed to describe. Is its job to explain change in time, or is it to describe the timeless, logical structure of the world? For now, the idea that time may be an emergent illusion remains a profound and controversial frontier of physics. It may be that our human intuition, honed by evolution to survive in a middle world of medium-sized objects, is simply incapable of grasping the true, timeless nature of reality that exists at the deepest levels. We are creatures of time, trying to understand a universe that may ultimately have no need for it. But our journey into the cosmos's deepest mysteries doesn't end with the abstract nature of time. It continues into the very architecture of space itself, where we find not a uniform distribution of matter, but a landscape of breathtaking emptiness. Truth number 15 reveals one of the most startling structures ever discovered. A region of space so vast and so profoundly empty that it defies all our expectations of how the universe should be organized. This is the Boötes void, a spherical chasm in the cosmos measuring an almost incomprehensible 330 million light-years across, a place where galaxies are almost absent, a true desert in the star-filled ocean of the universe. To truly grasp the scale of this void, we need to first appreciate the context of the cosmic web. We often picture the universe's large-scale structure as a vast network, a cosmic web of filaments where galaxies cluster together like glittering cities, connected by faint bridges of stars and gas with enormous, empty voids between them. This is the standard model, but the Boötes void is not a standard void. It is a supervoid, a cosmic anomaly of staggering proportions. If you were to place our Milky Way galaxy at the center of this void, the night sky would be nearly black. The closest major galaxy would be so far away that it would be barely visible to the naked eye, a single, faint smudge in an ocean of darkness. For most of astronomical history, we would have had no idea that other galaxies even existed. The discovery of this immense nothingness came about in the 1980s, when astronomers Robert Kirshner and his colleagues were conducting a large-scale survey of galaxy redshifts, which allowed them to map the three-dimensional positions of galaxies in the direction of the constellation Boötes, the herdsman. They expected to find a fairly even distribution, a cosmic foam. Instead, they found a staggering gap, a spherical region of space vast enough to contain thousands of galaxies like our Milky Way held almost none. Initially, only a handful of galaxies were found within its terrifying expanse, leading to its popular nickname, the Great Nothing. Refined observations have since increased the count to around 60 galaxies scattered throughout the void, but that number only deepens the mystery rather than solving it. In a region of space that size, based on the average density of the universe, we would expect to find at least 2,000 galaxies and likely many more. The fact that there are only about 60 means the Boötes void is about 250 times emptier than the rest of the known universe. These aren't just slightly underdense regions. This is a cavern of almost pure vacuum on a scale that challenges our understanding of cosmic evolution. So how does such a structure form? How can gravity, which pulls matter together, leave behind a hole so large and so empty? The prevailing theory points back to the very earliest moments of the universe, to those tiny fluctuations in the cosmic microwave background we discussed earlier. These quantum ripples were the seeds for all structure. The slightly denser regions grew into galaxy clusters and superclusters. The slightly less dense regions evolved into the voids we see. But the Boötes void is an extreme outlier. It suggests that in that initial distribution, there must have been an enormous region that was significantly less dense than its surroundings. As the universe expanded over billions of years, the matter from this underdense region continued to flow outward, drawn by the stronger gravitational pull of the denser filaments and knots of the cosmic web surrounding it. It's as if the void was carved out by gravity itself, which emptied it even further by siphoning its already scarce matter towards the denser regions outside. This makes the Boötes void not just an empty space, but an active participant in the cosmic dance. Its immense gravity, or rather, its profound lack of it, actually has a measurable effect on light passing through it. According to general relativity, light gains energy when falling into a gravitational well and loses energy when climbing out. But a void is the opposite of a well, it's a hill. Photons from the cosmic microwave background radiation that have to travel across the Boötes void experience a slightly different journey. As they enter the void, they must climb out of the gravitational potential of the dense surrounding areas, which causes them to lose a tiny amount of energy, redshifting the light slightly. Then, as they exit the void and fall back into the denser universe, they regain that energy. This phenomenon, known as the integrated Sachs-Wolf effect, is a direct, observable consequence of the void's existence and its impact on the fabric of space-time. The existence of such a colossal void forces cosmologists to re-examine their models. Does the standard model of cosmology, with its specific recipe of dark matter and dark energy, naturally produce voids this large and this empty? Or is the Boötes void a statistical fluke, a rare but possible feature in an otherwise predictable cosmos? Its discovery reminds us that the universe, for all its underlying laws, is also a place of immense variation and surprise. We have mapped the cosmic web, but we are still finding its most extreme continents and its most desolate deserts. The Great Nothing is a testament to the fact that emptiness is not merely the absence of something. It is a physical structure with its own properties, its own gravity, and its own story to tell about the evolution of everything. And if the cosmic voids reveal the architecture of emptiness on the largest scales, our next truth exposes a universe that is deeply, intimately connected in a way that defies all conventional logic. Truth number 16. Two particles can become so profoundly linked that a change to one, anywhere in the universe, instantly influences the other, a phenomenon so bizarre that even Albert Einstein himself rejected it, famously dismissing it as spooky action at a distance. This is quantum entanglement, and it's not just a theoretical curiosity. It's a proven feature of reality that challenges our most basic assumptions about space, time, and the very nature of existence. The story begins in the 1930s as the new and bizarre rules of quantum mechanics were being hammered out. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, sought to expose what they saw as a fundamental flaw in the quantum description of reality. They devised a clever thought experiment, now known as the EPR paradox, to prove that quantum mechanics must be an incomplete theory. The argument centered on a pair of particles that interact and become entangled. According to quantum theory, you could create two particles whose properties are perfectly correlated. For instance, you could have two electrons whose spins are linked. The math says that their combined spin must be zero, meaning if one is spinning clockwise, the other must be spinning counterclockwise. But here's the catch: according to quantum rules, neither particle has a definite spin until it is measured. They both exist in a fuzzy, probabilistic superposition of both possible states. Now, imagine separating these two entangled particles by a vast distance, sending one to a lab on Earth and the other to a lab on a planet orbiting a star in another galaxy. A physicist on Earth measures the spin of her electron and finds it to be clockwise. At that exact instant, she knows with 100% certainty that the other electron, billions of light years away, must now have a spin of counterclockwise. The question that troubled Einstein was this: how does the distant particle know to instantly assume the opposite state? It seems as if information about the measurement result has been transmitted from one particle to the other faster than the speed of light, a clear violation of the cosmic speed limit set by Einstein's own theory of relativity. He argued that this spooky, instantaneous connection was impossible and that there must be some deeper, hidden reality, hidden variables, that predetermined the particle states all along, making the correlation seem magical when it was actually just a pre-arranged agreement. For decades, this remained a philosophical debate, a battle between two titanic interpretations of reality. On one side was Einstein, defending a universe of local realism, where objects have definite properties and no influence can travel faster than light. On the other was the mainstream quantum view, championed by Niels Bohr, which accepted that particles don't have definite properties until measured, and that the universe is fundamentally non-local, with deep, invisible connections that transcend space. The debate seemed unresolvable, a matter of pure interpretation. That is, until a brilliant physicist named John Stuart Bell came along in the 1960s. Bell found a way to translate the philosophical argument into a real, testable experiment. He devised a mathematical inequality, now called Bell's inequality, that would be satisfied if Einstein's hidden variables were correct, but would be violated if the spooky, non-local quantum connection were real. The experiments began, most famously by Alain Aspect and his team in France in the 1980s. They created pairs of entangled photons and sent them flying off in opposite directions to detectors several meters apart. At the last possible moment, as the photons were in flight, the experimenters would randomly and quickly change the orientation of the detectors. This crucial step closed any potential loophole that could allow the particles to communicate by any conventional means at the speed of light or slower. The results were clear and decisive. Bell's inequality was violated. The particles were correlated in a way that no local hidden variable theory could ever explain. The change in one detector instantly influenced the outcome at the other, even though there was no time for any signal to travel between them. Spooky action at a distance was not a flaw in quantum theory. It was a feature of our universe. So what is actually happening? It's vital to understand what this is not. This is not information transfer. You cannot use entangled particles to send a message faster than light. The reason is that the outcome of the measurement on each side is completely random. The physicist on Earth measures her particle and gets a random result, say, clockwise. She instantly knows the state of the distant particle, but the person holding that distant particle has no idea that anything has changed. If they measure their particle, they also just get a random result counterclockwise. They have no way of knowing if their result was determined by their partner's measurement or if it was just random chance. It's only when the two experimenters get back together later, using a slow, classical communication channel like a radio signal, and compare their logs that they see the perfect, spooky correlation. So, while the influence is instantaneous, it cannot be used for faster-than-light communication. The universe, it seems, prevents time travel and paradoxes with a clever loophole of its own, the randomness of quantum outcomes. The implications of entanglement are nothing short of revolutionary for our understanding of reality. It suggests that the universe is not a collection of separate, independent objects. At a fundamental level, reality is deeply interconnected in a way that makes a mockery of the empty space between things. Those two entangled particles, once connected, do not behave as two individual entities but as a single, unified quantum system, no matter how far apart they are dragged. Space is not a barrier, it is almost an illusion. This non-locality forces us to reconsider the very idea of separateness. We are used to thinking of the universe as a stage where distinct objects interact. Entanglement suggests the stage itself is a participant, woven from a fabric of invisible threads that instantly tie distant events together. This bizarre property isn't just a laboratory curiosity. It is the foundation for emerging technologies like quantum computing and quantum cryptography. A quantum computer uses entangled quantum bits or qubits to perform calculations in parallel across a shared state. offering the potential to solve problems that are utterly intractable for even the most powerful classical supercomputers. Quantum cryptography uses the principles of entanglement to create communication channels that are fundamentally secure. Any attempt to eavesdrop on the quantum key distribution would immediately disturb the delicate entangled state, alerting the users to the presence of an intruder. We are moving from merely observing this spooky phenomenon to actually harnessing it, building the first machines that operate on the principles of this deeper, connected reality. Einstein was wrong about quantum entanglement being a sign of an incomplete theory, but his spooky label has stuck because it perfectly captures the sheer weirdness of it all. It is a concept that feels alien to our everyday experience, where objects are separate and influences travel no faster than sound or light. Yet, experiment after experiment confirms that this is how the universe works at its most fundamental level. It reveals a cosmos that is not a cold, empty void dotted with isolated islands of matter, but a single, intricately woven tapestry where every thread, no matter how far apart, remains connected in ways we are only beginning to comprehend. We've just explored the universe's bizarre interconnectedness, a realm where particles ignore the vast distances between them. But what if that interconnectedness is a clue to an even deeper secret about reality's very structure? This brings us to truth number 17, an idea so profound it seems ripped from the farthest reaches of science fiction. Our universe, in all its rich, three-dimensional glory, might be nothing more than a hologram, a spectacularly detailed projection from a flat, two-dimensional surface trillions of miles away. This is the holographic principle, and it's not a metaphor. It's a serious framework emerging from the most perplexing problems in black hole physics and information theory. The story begins not with holograms, but with a paradoxical question about black holes. What happens to information when something falls in? As we discussed earlier, Stephen Hawking discovered that black holes aren't completely black. They slowly radiate away their mass and eventually evaporate. This created the infamous black hole information paradox. The laws of quantum mechanics insist that information cannot be destroyed. If you burn a book, the information in its pages is not gone. It's just chaotically encoded in the smoke and ashes. In principle, with a perfect understanding of physics, you could reverse the process and reconstruct the book. But a black hole presented a terrifying problem. If you throw that same book into a black hole, it seems the information is irretrievably lost behind the event horizon. When the black hole finally evaporates, all that remains is the random thermal Hawking radiation, which appears to carry no information about what fell in. The book and its information are gone forever. This violated a fundamental pillar of quantum theory, suggesting our understanding of physics was deeply flawed. In the 1990s, a crucial insight came from a physicist named Gerard T. Hooft, later expanded by Leonard Susskind. They argued that the information isn't lost, it's not even inside the black hole. Instead, it is somehow encoded on the black hole's event horizon, its two-dimensional boundary surface. Think of the event horizon like a sphere surrounding the singularity. T. Hooft proposed that every single bit of information about everything that falls into the black hole, every atom of that book, every detail of its story, is imprinted onto this surface like pixels on a gigantic cosmic screen. The three-dimensional reality of the objects inside the black hole is a projection of the information stored on its two-dimensional boundary. This idea resolved the information paradox. When the black hole evaporates and emits Hawking radiation, that radiation can carry the information away because it's ultimately being read out from the event horizon's surface. The information was never truly inside, it was always on the surface. This revelation about black holes was groundbreaking, but the next logical leap was truly universe-shattering. If the description of a three-dimensional volume of space can be perfectly encoded on its two-dimensional boundary, could the same principle apply to the entire cosmos? Could our entire universe, with its galaxies, stars, planets, and ourselves, be nothing more than a projection from a two-dimensional surface at the very edge of the observable universe? This is the core of the holographic principle. It suggests that all the information that makes up our three-dimensional reality, every sight, sound, and sensation, is actually stored on a remote, vast two-dimensional surface. We are the hologram. To grasp this, think of an ordinary security hologram on a credit card. It's a flat, two-dimensional plastic film, but when light shines on it, it projects a three-dimensional image. The entire 3D image is contained within the encoded information on the 2D surface. The holographic principle proposes that the universe operates in a similar way. The surface is the boundary of the observable universe, and the light is the complex laws of physics that decode that information into the reality we experience. In this view, the universe we perceive is a magnificent illusion, a computational output generated from a cosmic code written on a distant two-dimensional shell. This isn't just philosophical speculation. It has a concrete mathematical basis rooted in the physics of black holes. The amount of information or entropy that a region of space can contain is not proportional to its volume, as you might expect, but to the area of its boundary surface. This is known as the Bekenstein-Hawking bound. For a black hole, its maximum entropy, the maximum amount of information it can contain, is precisely proportional to the area of its event horizon, not the volume of the singularity inside. This was the first solid clue that the fundamental description of a space might reside on its surface, not within its bulk. The holographic principle takes this concept and universalizes it, applying it to all of space-time. Imagine the implications. Every person you meet, every star you see, every emotion you feel, could be the holographic projection of information encoded on a flat surface so far away that light from the beginning of the universe hasn't even had time to reach it yet. Your brain processing this 3D reality is itself part of the projection. It's a dizzying, almost solipsistic thought, but it emerges from the hard math of quantum gravity. It provides a potential pathway to unify the seemingly incompatible worlds of general relativity, which describes the large-scale structure of space-time, and quantum mechanics, which describes the subatomic world. In the holographic description, gravity in the three-dimensional bulk emerges from the quantum physics operating on the two-dimensional boundary. This is often described by the AD-S/CFT correspondence, a specific mathematical duality that shows a correspondence between a gravitational theory in an anti-de Sitter space and a conformal field theory on its boundary. While the full holographic principle remains a conjectural framework and not a proven fact, it represents one of the most profound shifts in how we conceptualize reality. It tells us that the universe might be far stranger and more deeply interconnected than we ever imagined. The solidity of the world around us, the very sense of depth and dimension, could be an emergent property of a deeper, simpler, and fundamentally two-dimensional reality. We are not just living in the universe, we are a projection of its ultimate boundary, a cosmic hologram of breathtaking complexity, wondering at the image in the mirror. And if the holographic principle stretches our concept of reality to its absolute limit, our next truth brings us back to the astonishing and tangible diversity of worlds within our own cosmos. Truth number 18. There is a planet 5,000 light-years away in the constellation Serpens that is quite literally a diamond of unimaginable size and value. This isn't a poetic description, it is a scientific conclusion. The planet, known as PSRJ 1719-1438b, is likely a gigantic crystalline gem, a remnant of a once mighty star that has been crushed and transformed into a sphere of solid diamond. The story of this extraordinary world begins not with a planet but with the death of a star. Most stars in the universe are part of binary systems, two stars locked in a gravitational dance. The diamond planet story involves such a pair. The primary star in this cosmic duet was a massive star that lived its life and eventually died in a supernova explosion, leaving behind an ultra-dense, rapidly spinning core known as a pulsar. A pulsar is a type of neutron star. It's the crushed remnant of a star, a city-sized object with more mass than our Sun, spinning hundreds of times per second and blasting out beams of intense radiation like a celestial lighthouse. It was this pulsar, PSRJ 1007-11438, that astronomers were studying when they noticed a slight, rhythmic wobble in its incredibly precise spin. This tiny anomaly was the telltale signature of a companion object tugging on it, an exoplanet orbiting the pulsar. But this was no ordinary planet. The characteristics of its orbit revealed an object with a density far greater than any terrestrial world like Earth. Further analysis pointed to a breathtaking composition. Astronomers concluded that the planet is the leftover core of the pulsar's former binary partner, a white dwarf star that ventured too close. A white dwarf is the Earth-sized, super-dense core of a Sun-like star that has exhausted its nuclear fuel. It's made primarily of carbon and oxygen, the ashes of nuclear fusion. In most cases, a white dwarf and a pulsar can orbit each other peacefully for eons. But in this system, the orbit decayed. The white dwarf spiraled inward, crossing a point of no return known as the Roche limit. As it did, the immense tidal gravity from the pulsar began to strip away the star's outer layers, shredding it down to its incredibly dense core. What remained was a planet-sized object, but one with a truly staggering density. Calculations show it has a mass just slightly greater than that of Jupiter, but its physical size is less than half of Jupiter's, and in fact, it's not much larger than Earth. This means it is incredibly compact, given its known mass and size and its origin as a white dwarf core. The only substance dense enough to account for these properties is crystalline carbon, a diamond. The intense pressure from the pulsar's gravity has compressed the carbon core of the former star into a gigantic crystal lattice. This world is, for all intents and purposes, a single diamond of almost pure carbon, likely surrounded by a thin layer of graphite. It completes a full orbit around its pulsar parent in just 2 hours and 10 minutes, a dizzying dance that speaks to its incredibly close and violent history. Now, the question of its value is a fun, though ultimately fanciful, exercise that highlights its sheer extravagance. The estimated mass of the diamond planet is about that of Jupiter, which is 318 times the mass of Earth. If we take just a single cubic centimeter of diamond on Earth and extrapolate its value to this scale, the number becomes absurd. The figure often quoted is $26.9 nonillion. A nonillion is a 1 followed by 30 zeros. To write that out, it would be $26,900,000,000,000,000,000,000,000,000. This number is so vast it becomes meaningless, dwarfing the entire gross domestic product of our planet for all of human history by an incalculable factor. Of course, this valuation ignores the fundamental laws of economics. Introducing that much diamond into any market would instantly make diamonds worthless, as their value is based on their artificial scarcity. But the mental image is powerful. A single world whose raw material value is a number so large it defies any human context for wealth. The existence of such a world is a stunning demonstration of the universe's capacity for creating extremes. It shows us that the category of planet is far more diverse and wondrous than we once imagined. We have gas giants, ice giants, rocky worlds, and now a confirmed gemstone world. It proves that the processes of stellar evolution and destruction can leave behind relics of breathtaking and bizarre beauty. The diamond planet is not just a celestial curiosity. It is a fossil record of a violent and intimate stellar relationship, a monument to the fact that even in death, stars can create objects of unimaginable splendor. While we marvel at the universe's capacity to forge worlds of diamond, there are far larger and more mysterious forces at work, orchestrating the grand ballet of galaxies across the cosmos. This brings us to truth number 19, a sobering reminder of how much we still don't control or even fully understand. Our entire galactic neighborhood is being pulled against its will toward a mysterious and unseen gravitational behemoth hidden deep in the shadows of our own sky. This colossal force is known as the Great Attractor, and it's tugging our local group of galaxies toward it at an astonishing 600 kilometers per second. Our journey to this discovery begins close to home with the apparent motion of our galaxy through the universe. For a long time, we've known that our Milky Way and our nearest large galactic neighbor, the Andromeda Galaxy, are gravitationally bound, destined to collide in billions of years. This entire collection, known as the local group, is itself just a small part of a much larger structure, the Virgo supercluster, a vast collection of thousands of galaxies. In the 1970s, as astronomers began mapping the velocities of galaxies on an ever grander scale, they noticed something peculiar. When they subtracted out the overall expansion of the universe, the Hubble flow, they found a significant residual velocity. Our entire local group wasn't just moving randomly, it was clearly being pulled in a specific direction toward the constellations of Centaurus and Hydra, far beyond the Virgo cluster. The sheer speed of this motion was staggering. We are being pulled at over 2 million kilometers per hour toward something with a gravitational pull so immense it can dominate an entire region of the universe millions of light years across. The quest to identify the source of this pull led astronomers to name it the Great Attractor, but finding it proved to be an immense challenge because it lies directly behind the plane of our own Milky Way galaxy, in a region astronomers call the zone of avoidance. This isn't a place of actual avoidance, but one of extreme obstruction. The galactic plane is packed with stars, gas, and immense clouds of dust that effectively create a visual brick wall, blocking our view of the universe beyond in that specific direction. It's like trying to see a distant city while standing in the middle of a dense, foggy forest. The trees and fog in the foreground completely obscure your view. For decades, the Great Attractor remained one of astronomy's great enigmas, a ghost in the cosmic machine whose presence we could feel but not see. The breakthrough began with new technology that allowed us to see through the galactic fog. While visible light is blocked by the dust, longer wavelength radiation, such as radio waves and infrared light, can penetrate it. Surveys using powerful radio telescopes like the Parkes Observatory in Australia began to pierce the zone of avoidance, painstakingly mapping the hidden galaxies behind the Milky Way's central bulge. What they revealed was a monumental structure, a gravitational anchor worthy of the name. The Great Attractor isn't a single, impossibly dense object. Instead, it is the heart of an even larger supercluster of galaxies, now known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, is our true cosmic address. It is a galactic filament containing over 100,000 galaxies, including our own Virgo supercluster, all flowing along invisible gravitational watersheds toward a common center of mass, the Great Attractor region. This region is dominated by a massive cluster of galaxies called the Norma cluster, which is itself surrounded by other enormous clusters and vast concentrations of mass, including the weighty Centaurus cluster. The combined gravity of all this normal matter, however, still wasn't enough to fully account for the immense pull we experience. Just as with the rotation of individual galaxies, dark matter is almost certainly the hidden hand here, providing the bulk of the gravitational glue that makes the Great Attractor so powerful. So, while we now know the general location and nature of this cosmic landmark, its full details remain shrouded. It is the gravitational core of our local universe, the central valley in the watershed of galaxies to which we all flow. This relentless motion puts our place in the cosmos into a humbling perspective. We are not stationary observers on a calm sea. We are passengers on a galactic ship caught in a powerful current, pulled toward a destination we once couldn't see, reminding us that even on the grandest scales, we are subject to forces far greater than ourselves, moving through a universe whose deepest structures are still being mapped. But if the great attractor shows us the immense pull of hidden mass, the true nature of that pull is even more bizarre than a simple invisible force. Truth number 20 rewrites our entire understanding of gravity itself, revealing it is not a force that reaches out across space, but rather the curvature of the very stage upon which the cosmic drama unfolds. According to Albert Einstein's general theory of relativity, gravity is the warping of space and time by mass and energy. The universe isn't a static arena with actors pushing and pulling on each other. The actors themselves bend and twist the stage, and what we perceive as gravity is simply other actors following the curves and contours of that bent landscape. The most powerful way to visualize this mind-bending concept is through the famous rubber sheet analogy. Imagine the entirety of space-time as a vast, taut, horizontal rubber sheet. This two-dimensional sheet represents the three dimensions of space and one of time woven together into a single fabric. Now, place a heavy bowling ball in the center of this sheet. What happens? The weight of the ball creates a deep, curved indentation in the rubber. The fabric is warped. This is exactly what a massive object like our sun does to the fabric of space-time. It creates a gravity well, a curvature that dictates how other objects move. Now take a much smaller, lighter object like a marble and set it rolling across this taut sheet. If you roll it far from the bowling ball where the sheet is still flat, the marble will travel in a straight line at a constant speed, following the natural, uncurved geometry of the sheet. This is an object in empty space, feeling no gravitational influence. But if you roll the marble so that it passes near the indentation created by the bowling ball, its path will change dramatically. It won't be pulled by an invisible string from the ball. Instead, it will simply follow the curvature of the dent. The marble might curve around the bowling ball, perhaps even entering a stable circular or elliptical orbit around it, forever trapped rolling around the sides of the gravity well. From above, it looks like the bowling ball is attracting the marble, but in reality, the marble is just following the shortest possible path, a geodesic through the warped geometry it finds itself in. This is the essence of Einstein's revolution. The Earth orbits the Sun not because the Sun is reaching out with invisible tentacles of force to pull on us, but because the Sun's immense mass has warped the space around it, and our planet is simply following the curved path of that warp. Even the path of light itself is bent by this curvature. A beam of light from a distant star passing very close to the Sun will have its trajectory bent as it travels through the warped space around it, causing the star's apparent position in the sky to shift. This prediction was confirmed during a solar eclipse in 1919, making Einstein a global celebrity and solidifying one of the greatest intellectual achievements in human history. The rubber sheet analogy, while incredibly useful, does have its limits. It only shows the warping of space, but in reality, Einstein showed that time is also warped by gravity. A massive object doesn't just bend the fabric of space, it also causes time to run slower the closer you get to it. This is why the clocks on GPS satellites higher up in Earth's gravitational well run faster than clocks on the surface. So the full picture is a four-dimensional warping of space-time, a concept that is notoriously difficult to visualize but is precisely described by Einstein's beautiful, complex equations. This idea transforms our view of the cosmos from a mechanistic push and pull to a dynamic, geometric dance. The planets are not being forced into orbit, they are surfing the gentle, curved slopes of the Sun's gravity well. A black hole is simply an object so massive and dense that it warps space-time into an infinitely deep pit, a well so steep that not even light has enough energy to climb out. The serene, elegant orbits of celestial bodies are a direct result of the invisible topography of the universe, a landscape of hills and valleys carved by mass where every object moves according to the lie of the land. But this 1.3-second delay for our closest cosmic neighbor is just the very beginning of a far more profound principle that defines our entire view of the cosmos. The truth is, we are never seeing anything in the universe as it is right now. We are always looking into the past. The farther away an object is, the deeper into history we are gazing. This transforms our telescopes from mere instruments of observation into the most powerful time machines ever conceived. Every time we look up, we are engaging in a form of cosmic archaeology, peeling back layers of time to witness the universe's long and intricate history. Consider the Sun itself. It sits a comfortable 93 million miles away, a distance so vast that its light takes a full 8 minutes and 20 seconds to cross the void and reach our eyes. This means that if the Sun were to suddenly, inexplicably vanish at this very instant, we on Earth would continue to bask in its warmth and light for another 8 minutes, completely unaware of the catastrophe. We wouldn't see it disappear from the sky until the last photon it emitted finally completed its journey. The Sun we see is not the Sun of now, it is the Sun of 8 minutes ago. Now extend this concept outward. The brilliant star Sirius, the brightest in our night sky, is about 8.6 light-years away. The sparkle we see tonight left the surface of that star when you were likely much younger, a child perhaps, and has been traveling through the emptiness of space ever since, only just arriving at your eye. The famous Orion Nebula, a stellar nursery where new stars are being born, is about 1,300 light-years distant. The glorious, gaseous tapestry we photograph is a snapshot from the time of the fall of the Roman Empire. We are witnessing cosmic events that occurred while emperors ruled and ancient civilizations rose and fell, their light only just now reaching us. This phenomenon, known as look-back time, reaches its most awe-inspiring scale when we point our most powerful telescopes at the farthest edges of the observable universe. The Hubble Space Telescope's iconic deep-field images, which revealed thousands of galaxies in a patch of sky that once seemed empty, are showing us galaxies as they were over 13 billion years ago. We are seeing them not as the majestic, mature spirals they may be today, but as they were in their cosmic infancy not long after the Big Bang itself. We are witnessing the universe as a toddler, and in doing so, we are directly observing the process of galaxy formation and the early, chaotic chapters of cosmic history. The James Webb Space Telescope pushes this even further, peering back to within a few 100 million years of the beginning, to a time when the first stars and galaxies were beginning to ignite, ending the cosmic dark ages. This creates a bizarre and humbling map of the heavens. The night sky is not a flat, two-dimensional painting. It is a deep, multi-layered historical record. When you look up, you are seeing the moon from 1 second in the past, the sun from 8 minutes in the past, nearby stars from years or decades ago, and distant galaxies from millions or billions of years in the past. All of these events from different epochs are presented to your eyes simultaneously, creating a collage of cosmic history. You are, in a very real sense, surrounded by ghosts, the light of objects that may have changed dramatically or even ceased to exist by the time their ancient light finally tells us their story. Our view of the cosmos is a magnificent tapestry woven from threads of different ages, a constant and beautiful reminder that to look out into space is to look back into time. While our own solar system presents a fascinating array of worlds, from the swirling storms of Jupiter to the frozen plains of Pluto, the true extremes of planetary weather are found light years away, on worlds that defy every Earth-based expectation. This brings us to truth number 22, a forecast so violent it sounds like a line from a science fiction nightmare. On a deep blue planet known as HD 1897-33b, The atmosphere is so hostile that it rains molten glass sideways in hyper-hurricane winds that scream across the sky at over 5,000 miles per hour. Discovered in 2005 orbiting a star 65 light-years away in the constellation Vulpecula, the Fox HD 1897-33b was one of the first exoplanets to have its atmosphere directly analyzed. From a distance, it appears as a beautiful, deep azure marble, a color reminiscent of our own oceans as seen from space, but this serene appearance is a cosmic deception. This is not the blue of liquid water, but the blue of a scorching, hazy atmosphere thick with silicate particles, the very stuff that makes up glass on Earth. The planet is a classic example of a class of worlds known as hot Jupiters. It is a gas giant, slightly more massive than our own Jupiter, but it orbits so impossibly close to its parent star that its year is just 2.2 Earth days. This proximity creates a state of tidal locking, meaning one side of the planet permanently faces the star, broiling under endless, scorching daylight, while the other side is trapped in eternal, frigid night. The temperature difference between these two hemispheres is nothing short of apocalyptic. The dayside temperature soars to a searing 1,700 degrees Celsius, hot enough to melt iron and vaporize rock. The night side, while cooler, is still a blistering several hundred degrees. It is this extreme temperature gradient that fuels the planet's unimaginable weather. On Earth, weather is driven by the sun's uneven heating of the surface, creating air currents that move from high to low pressure. On HD 1897-33b, this process is dialed up to a level of pure fury. The atmosphere acts as a giant heat engine, trying desperately and violently to redistribute the immense heat from the dayside to the night side. This results in supersonic winds racing from the day hemisphere to the night hemisphere, with estimated speeds reaching an astonishing 8,700 kilometers per hour or 5,400 miles per hour. This is over 7 times the speed of sound on Earth and nearly 20 times the wind speed of the most powerful hurricanes our planet has ever recorded. Now imagine the rain in this maelstrom. The dayside heat is so intense that it doesn't just melt silicate rock, it vaporizes it, creating a high-altitude haze of silicate particles in the atmosphere. As these tiny droplets of molten rock and glass are carried by the supersonic winds toward the marginally cooler night side, they begin to condense and coalesce, forming larger droplets. But there is no gentle falling here. The particles are whipped horizontally by the relentless winds, creating a permanent, planet-wide storm of raining glass that flies sideways, scouring the atmosphere in a horizontal blizzard of cutting, molten shards. Any hypothetical visitor would be instantly flayed and vaporized, their atoms shredded and incorporated into the hellish atmospheric cycle. The discovery of such a world fundamentally changes our understanding of what a planet can be. It shatters our parochial, Earth-centric view of weather as something involving water droplets, snowflakes, or dust storms. It reveals that the physical processes we understand, evaporation, condensation, precipitation, are universal, but the materials involved are limited only by a planet's composition and its place in the solar system. The universe can forge storms of methane on Titan, blizzards of carbon dioxide on Mars, and hurricanes of molten silicon on distant gas giants. HD 1897-33b is a stark reminder that the cosmos is not just a more vast version of our local environment. It is a laboratory of extreme physics, capable of creating environments of both breathtaking beauty and unimaginable violence, often in the very same place. For centuries, a cornerstone of cosmology has been the cosmological principle, the idea that on the largest scales, the universe is isotropic and homogeneous. This means it should look roughly the same in every direction and from every location. There should be no special place, no center, and no preferred direction. This principle is the bedrock upon which we've built our entire understanding of the cosmos, from the Big Bang model to the expansion of space itself. But what if this fundamental assumption is wrong? What if the universe, after all, has a preferred direction? This startling possibility emerges from a subtle anomaly in the oldest light we can see, the cosmic microwave background. The CMB is famously uniform, a near-perfect blackbody glow at 2.7 degrees Kelvin. But when we look with extreme precision, we find its temperature is not perfectly even. It has a dipole anisotropy. Simply put, the CMB appears very slightly warmer in one direction of the sky and very slightly cooler in the exact opposite direction. The difference is tiny, only about 3.3 thousandths of a degree Celsius, but it's unmistakable. For decades, the standard explanation for this has been straightforward. It's our own motion. Just as an ambulance siren sounds higher-pitched as it moves toward you and lower-pitched as it moves away. The Doppler effect. The CMB photons appear warmer and more energetic in the direction we're heading and cooler in the direction we're leaving behind. This CMB dipole allowed us to calculate our solar system's velocity relative to this primordial rest frame. We're moving at about 630 kilometers per second toward the constellation Centaurus, caught in the gravitational currents of the local group, the Virgo cluster, and the Great Attractor. But here's where the plot thickens. If the CMB dipole is entirely due to our motion, then that same motion should imprint itself on every other large-scale structure in the universe. The light from distant galaxies and quasars, the distribution of galaxy clusters, all of it should show a similar dipole pattern aligned with the one in the CMB, because it's all being observed from our moving platform. Yet, several recent and ambitious sky surveys are finding something deeply puzzling. When astronomers map the distribution of hundreds of thousands of quasars or galaxies across billions of light years, they are detecting a dipole in their number counts and their properties. And this dipole appears to be aligned with the CMB dipole, but it is significantly larger, much larger. The observed velocity from these surveys would require us to be moving at speeds far greater than what the CMB indicates. This is a major contradiction. It suggests that not all of the CMB dipole can be explained by our local motion. A portion of it might be intrinsic to the CMB itself, a genuine lopsidedness in the universe's structure from its very beginning. This is where we encounter a phrase that cosmologists find both provocative and troubling, the axis of evil. This was the name given to a set of other, more peculiar alignments found in the CMB data. Beyond the simple dipole, the quadrupole and octupole moments of the CMB, the next levels of detail in its fluctuations appear to be oddly aligned with each other and with the plane of our solar system. This is deeply strange. The patterns in the primordial universe, the blueprint for all cosmic structure, should have no correlation whatsoever with the arbitrary orientation of our tiny, local planetary system billions of years later. It would be like finding that the foundation plan for a city was mysteriously aligned with the floorboards in your own living room. The chance of this being a random fluke is very small. It suggests a systematic error in our measurements, or far more excitingly, a crack in the cosmological principle itself. So what could this mean? The implications are profound. If the universe is not isotropic, it challenges the very foundation of modern cosmology. It could mean that the universe is rotating on a grand scale, that it has a large-scale magnetic field influencing structure, or that our universe is part of a larger multiverse and we are seeing the gravitational tug of a neighboring cosmos. The most conservative explanation is that these are all unconnected statistical flukes, or more likely, subtle systematic errors in our observations that we haven't yet identified and corrected for. But the persistence of these anomalies across different instruments and surveys is making that harder to dismiss. We are left with a haunting possibility that we are not just moving through space, but that the universe itself might be tilted, pointing in a direction that, for now, we can only call its preferred axis. But if the axis of evil hints at a universe that isn't as uniform as we thought, our next truth presents a concept so perfectly symmetric it feels mathematically inevitable, yet so bizarre we have no evidence it exists in reality. Truth number 24. The universe might contain the exact opposite of a black hole, a white hole, a region of space-time where matter and energy erupt outward in a dazzling fountain, a place where nothing can ever enter, only exit. This isn't just science fiction, it is a real, valid solution to the equations of general relativity, a cosmic idea that pushes our understanding of physics to its absolute limit. The story of white holes begins with the story of black holes, but played in reverse. When Carl Schwarzschild first solved Einstein's equations for a single, non-rotating point of mass, he found two solutions. One described the black hole we know and fear, a point of infinite density, a singularity surrounded by an event horizon, a one-way membrane from which nothing can escape. But the mathematics, being time-symmetric, also allowed for a second mirror solution. This second solution described a singularity that is not hidden behind an event horizon that things fall into, but one that is hidden behind a horizon that things emerge from. Imagine a black hole's movie played backward. Instead of matter collapsing inward past a point of no return, matter is spewing outward from a point of no admission. This is the white hole. Think of it like this: a black hole's event horizon is a river waterfall's edge. Once your boat goes over the lip, there's no rowing back upstream. A white hole's horizon would be like the base of that same waterfall, but with an impossible, supernatural current. Water is exploding upward with such ferocity that you could never hope to paddle your boat into the flow to reach the cliff above. You can only be pushed away. A white hole would be a cosmic gusher, an exhaust port for the universe, violently expelling matter and energy while forbidding any approach. The immediate and obvious question is, where would all this matter and energy be coming from? One of the most compelling, though highly speculative, theories connects white holes directly to the birth of our entire universe. Some physicists have proposed that the Big Bang itself could be interpreted as a white hole event. Instead of a singularity of infinite density existing before time, it was a white hole singularity from which all the matter and energy of our universe erupted. This would solve the problem of the initial singularity by reframing it not as the beginning of time, but as a gateway from another state or even another universe. In this view, our cosmos isn't expanding from a point in nothingness, but is the ongoing eruption from a white hole that initiated space and time as we know them. Another fascinating and equally speculative idea links white holes to the ultimate fate of black holes through quantum gravity. We discussed that black holes slowly evaporate via Hawking radiation over unimaginable eons. But what happens when that process finally completes? Does the black hole just vanish, leaving nothing behind? Some theories suggest that the final stage of black hole evaporation might not be nothingness but a quantum transition, a bounce. The collapsing black hole singularity could rebound, transforming into an expanding white hole singularity. However, because this transition would be governed by quantum effects, the resulting white hole might not be the colossal structure of the original black hole. It could be a microscopic white hole, a tiny puncture in space-time from which the information and energy of everything that ever fell into the black hole is finally, violently returned to the universe. It would be the black hole's death and rebirth in a new form, a cosmic recycling of the most fundamental kind. Despite their mathematical elegance, white holes face a colossal problem. They seem to violate the second law of thermodynamics. The universe has a powerful preference for disorder, for an increase in entropy. A white hole, by spewing out ordered, low-entropy matter and energy from a singularity, would appear to be a fountain of order, effectively decreasing the total entropy of the universe. This makes them seem fantastically improbable. Furthermore, we have never observed anything that remotely resembles a white hole. Any such object would be spectacularly bright, emitting staggering amounts of radiation across the spectrum as it expelled its contents. If one existed anywhere in our observable universe, our telescopes would almost certainly have seen it. So why do physicists still entertain the idea? Because the mathematics insists they are possible, and in theoretical physics, that is a powerful reason to listen. They represent a form of cosmic symmetry that is too beautiful to ignore. They force us to ask deeper questions about the nature of singularities, the arrow of time, and the very origins of our universe. They remind us that the solutions to Einstein's equations often contain hidden gems that predict realities far stranger than we could have invented on our own. While a white hole may never be found, the pursuit of understanding them illuminates the profound connections between gravity, time, and the quantum world, guiding us toward a more complete theory of everything. They are a breathtaking testament to the power of human thought, allowing us to conceive of cosmic wonders that may exist only in the pristine world of mathematics, yet forever expand our imagination of what is possible. Yet for all the colossal structures and bizarre cosmic forces we've explored, some of the most profound truths are delivered by the smallest, most elusive messengers, particles that barely acknowledge our existence. Truth number 25 reveals a stunning reality of our daily existence. Every single second of your life, day and night, you are being harmlessly pierced by trillions upon trillions of ghostly subatomic particles called neutrinos. They are streaming through your body right now, passing through the solid ground beneath your feet, and flying out the other side of the planet without a single interaction. A silent, invisible rain that connects you directly to the heart of distant stars and the most violent explosions in the universe. To understand the sheer scale of this bombardment, let's put some numbers to this phantom downpour. Scientists estimate that about 100 billion neutrinos from the Sun pass through every single square centimeter of your body every second. To put that in perspective, consider the tip of your finger. In the time it takes you to read this sentence, more neutrinos will have passed through that tiny area than there are grains of sand on all the world's beaches. They are the second most abundant particle in the entire universe after photons of light, outnumbering atoms by a factor of about 1 billion to 1. And yet, despite this unimaginable abundance, their presence was entirely unknown to science until the 20th century, and for a very simple reason: they almost never stopped to say hello. This ghostly nature is due to two key properties. First, neutrinos are electrically neutral, which means they are completely unaffected by the electromagnetic force that governs most of our everyday interactions, from the light we see to the chemistry of our bodies. Second, they interact only via the weak nuclear force and gravity, and the weak force has an incredibly short range. This makes the neutrino a cosmic introvert, barely engaging with other matter. In fact, the average neutrino could pass through a light year of solid lead, a wall of metal over 5.8 trillion miles thick, without hitting a single atom. For a neutrino, our planet is less substantial than a wisp of smoke is to us. So how do we know they're even there if they're so elusive? Their existence was first proposed in 1930 by physicist Wolfgang Pauli as a desperate, almost apologetic solution to a perplexing problem. Scientists studying a type of radioactive decay called beta decay found that energy appeared to be missing from the reaction, seemingly violating the sacred law of energy conservation. Rather than abandon this fundamental principle, Pauli suggested that the missing energy was being carried away by a new, invisible, and nearly massless particle that was escaping their detectors. He reportedly said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He thought his idea was untestable, but he was wrong. It took another 26 years, but in 1956, Clyde Cowan and Frederick Rionese finally did the impossible. They detected the neutrino. Their ingenious experiment was placed next to a powerful nuclear reactor at the Savannah River plant in South Carolina, a prolific source of the particles. They used a massive tank of water surrounded by sensitive photon detectors. They reasoned that while almost all neutrinos would zip right through, a very few would, by sheer chance, strike a proton in a water molecule. This incredibly rare collision would produce a faint flash of light, a signature that could be picked up by their equipment. After years of painstaking work, they saw the flashes. The ghost had finally been caught, but where do all these countless trillions of neutrinos come from? Their origins are as diverse as the cosmos itself, painting a picture of a universe teeming with nuclear activity. The overwhelming majority that shower down on us are solar neutrinos produced in the core of our sun. Deep within its fiery heart, where pressures and temperatures are immense, protons are fused together to form helium in a process that powers the star. For every 4 protons fused into one helium nucleus, 2 neutrinos are released, carrying energy away from the reaction. These particles, born in that solar inferno, race outward at nearly the speed of light. Just 8 minutes after their creation, they arrive at Earth, a direct signal from the sun's powerful engine. Beyond our solar system, neutrinos are forged in even more dramatic cosmic cataclysms. When a massive star reaches the end of its life and collapses in a supernova explosion, an unimaginable burst of neutrinos is produced. In fact, 99% of the energy of a supernova is released not in light but in these ghost particles. When supernova 1987 exploded in the Large Magellanic Cloud, a neighboring galaxy, detectors on Earth picked up a handful of neutrinos a full 3 hours before the light of the explosion arrived. This wasn't because the neutrinos traveled faster than light, but because they could escape directly from the collapsing core immediately, while the visible light was trapped behind the shockwave for hours. This event marked the dawn of neutrino astronomy, proving that these particles could be used as messengers from the most violent events in the universe. Their role as cosmic messengers has only expanded. We now detect neutrinos from the violent environments around supermassive black holes, from the merging of neutron stars, and from the mysterious cosmic rays that bombard our atmosphere. They are the only particles that can travel in a straight, unhindered line from the deepest, most chaotic regions of the cosmos directly to our detectors, offering a clear view of processes that light, which can be absorbed, scattered, and bent, can never show us. By building enormous, sensitive detectors deep underground, like the Super Kamiok, an observatory in Japan, a tank containing 50,000 tons of ultra-pure water, surrounded by 13,000 light sensors, we are learning to read these messages from the ghost universe, a silent, invisible world that is constantly telling us the secrets of the stars. But if the silent reign of neutrinos showcases a universe of unshakable constants, our next truth threatens to pull that very foundation out from under us. What if the laws of physics themselves are not eternal and unchanging, but are instead in a state of gradual cosmic drift? This isn't a fringe idea. It's a serious proposition backed by startling astronomical observations that suggest one of the most fundamental numbers in nature, the fine structure constant, may not be so constant after all. If confirmed, this single finding wouldn't just add a new chapter to physics. It would burn the entire textbook and force us to write a new one from scratch. To understand why this is so revolutionary, we first need to appreciate what the fine structure constant is and why physicists have, for so long, revered it as a fixed pillar of reality. Represented by the Greek letter alpha, the fine structure constant is a pure number, approximately equal to 1 over 137. It's called a constant because it beautifully combines 3 other fundamental constants: the charge of the electron, the speed of light, and Planck's constant. This unique combination governs the strength of the electromagnetic force, which is responsible for holding atoms together, creating chemical bonds, and generating light. It dictates how tightly electrons are bound to an atomic nucleus and determines the very specific colors or spectral lines that each element emits when it's energized. Because it is a dimensionless number, a ratio without units, its value should be the same everywhere in the universe and at every point in time. It is the bedrock upon which the stability of matter is built. The first tantalizing and deeply controversial evidence that this bedrock might be shifting came from a team of astronomers led by John Webb in the late 1990s. They weren't looking for a revolution, they were simply using the world's most powerful telescopes to study the most ancient light we can access, the light from incredibly distant quasars. Quasars are the intensely bright cores of active galaxies, acting as cosmic lighthouses billions of light-years away. As this light journeys across the universe to reach us, it passes through immense clouds of interstellar gas. Atoms within these clouds absorb specific wavelengths of the quasar's light, creating a unique barcode of dark lines in the spectrum, an absorption spectrum that tells us exactly which elements are present in those clouds. Webb's team meticulously analyzed these spectral barcodes from quasars in opposite directions of the sky. When they looked at quasars in one direction, they found that the absorption lines for certain elements like iron and magnesium were not exactly where they were supposed to be. The lines were minutely shifted, as if the fine structure constant in those distant gas clouds had a slightly different value than it does here on Earth. The shift was tiny, a change in alpha of just a few parts in a million, but it was consistent. In one direction, the data suggested alpha was smaller in the past. In the opposite direction, it seemed to have been larger. This implied not only that the constant might be changing over time, but that the change might not even be uniform across space. The universe might have a preferred direction, a dipole, in the laws of physics themselves, echoing the strange alignments we see in the cosmic microwave background. The astronomical community met these claims with intense skepticism, as well they should. Extraordinary claims require extraordinary evidence. The measurements are at the very bleeding edge of our technological capabilities, and numerous potential sources of error could mimic such a subtle shift. Could it be systematic errors in the telescopes, unknown chemical processes in the early universe? For over 2 decades, other teams have tried to verify or refute Webb's findings using newer instruments and different methods. The results have been a mixed bag, with some studies supporting a variation and others finding no evidence at all. The debate is far from settled, but the mere possibility remains electrifying because of what it would mean for our understanding of reality. If the fine structure constant truly is variable, it unravels our entire conception of the universe. It would mean that the fundamental forces of nature have not always had their current strength. The electromagnetic force might have been slightly stronger or weaker billions of years ago. This has staggering implications. The entire process of nucleosynthesis inside stars is exquisitely sensitive to these forces. A slightly different alpha would change how stars burn their fuel, how they create heavy elements, and even whether they could explode as supernova. It could mean that the chemical elements necessary for life, the carbon, oxygen, and iron we are made of, were produced in different abundances in the past, or might not have been produced at all in some regions of the cosmos. The universe could be a patchwork of physical laws, with some regions hospitable to life as we know it and others utterly sterile. This idea of inconstant constants also provides a potential pathway to a deeper theory of everything. For a long time, physicists have wondered why the fundamental constants have the specific, life-permitting values that they do. The prevailing answer has been the anthropic principle. We find ourselves in a universe with these constants because they allow for our existence. But if the constants can vary, then this question transforms. Instead of asking why these values, we could ask what physical mechanism sets these values and how does it change over time. Some theories, like string theory, actually predict the existence of numerous scalar fields, dubbed dial fields, that could slowly evolve over cosmic time, subtly tuning the constants of nature as they change. The variation of alpha wouldn't be a flaw in the universe's design. It would be a feature, a dynamic process we are only just beginning to detect. we are left in a state of profound uncertainty, standing on the precipice of a potential paradigm shift. The constancy of the laws of physics is an assumption so deep that it underpins every single cosmological model. To question it is to question the very rules of the game. If the fine structure constant is indeed variable, then the universe is not a static arena with fixed rules. It is a dynamic, evolving entity whose most basic operating principles are themselves part of its history. We would be forced to see reality not as a clockwork mechanism, but as something far more organic and fluid, a cosmos where the rules themselves are written in fading ink, changing just slowly enough for structures like us to emerge and for a brief moment try to read them. But while the universe might hold the faint, sweet scent of raspberries and rum, it also has a far more potent bar serving up a truly staggering cocktail. Truth 27 reveals that floating near the center of our galaxy is a colossal cloud of gas and dust containing billions upon billions of liters of alcohol. Not just any alcohol, but a vast reservoir of vinyl alcohol alongside ethanol and other complex organic molecules. This isn't a celestial brewery, it's a natural chemical factory operating on an unimaginable scale, and its product is a key piece of evidence in the case for life's cosmic origins. The scene of this interstellar distillery is once again the incredible Sagittarius B2 molecular cloud. We've visited it before for its aroma, but its true significance lies in its profound chemical complexity. This cloud is a stellar nursery, a place where new stars are being born from the gravitational collapse of gas and dust. But within its frigid, dark reaches, where temperatures hover just a few degrees above absolute zero, an intricate dance of chemistry is taking place on the surfaces of tiny dust grains. These grains, made of silicates and carbon, act as cosmic catalysts. Simple, common atoms like carbon, oxygen, and hydrogen drift through the void and stick to these cold, dusty surfaces. Here, shielded from the harsh radiation that might break them apart, they can slowly shuffle around and link up, forming increasingly complex molecules. Over millions of years, this process builds molecules that are the direct precursors to the building blocks of life. The detection of vinyl alcohol here is particularly significant. On Earth, vinyl alcohol is a fleeting, unstable compound that quickly converts into other forms. But in the cold, low-pressure environment of deep space, it can form and persist. Its discovery in Sagittarius B2 was a milestone because it's what chemists call an enol. Enols are a specific type of molecule that are known to be important stepping stones in the formation of even more complex organic compounds, including amino acids, the very things that string together to form proteins, which are the workhorses of life as we know it. Finding it in such abundance in space tells us that the universe isn't just making simple molecules. It's following a sophisticated chemical pathway that naturally leads toward biological relevance. And vinyl alcohol is just one patron at this cosmic bar. Sagittarius B2's spectral signature reads like a chemical shopping list for probiotic ingredients. Astronomers have also identified enormous quantities of ethanol, the same alcohol found in alcoholic beverages, along with formaldehyde, hydrogen cyanide, glycolaldehyde, a simple sugar, and even amino acetonitrile, a direct precursor to the amino acid glycine. The scale is utterly mind-boggling. The cloud contains enough ethanol to create a volume of pure 200-proof liquor so vast that it could supply every single person on Earth with 300,000 pints of beer every day for the next billion years. The numbers are so large they become abstract, but they drive home a crucial point. The universe is not chemically barren. It is prolific, manufacturing the raw ingredients for biology long before planets even form. This changes everything about how we view the origins of life on our own planet. The classic primordial soup theory imagines lightning striking a mixture of simple gases in Earth's early atmosphere, jump-starting the chemistry of life. But the discovery of complex organics in space suggests a compelling alternative, or more likely, a powerful supplement: prebiotic seeding. When our solar system condensed out of a molecular cloud similar to Sagittarius B2 some 4.6 billion years ago, all of these pre-made organic molecules would have been incorporated into the mix. They became part of the protoplanetary disk, the swirling cloud of material that formed the Sun, the planets, and all the comets and asteroids. These molecules would have rained down on the early Earth aboard meteorites and comets, delivering a starter kit of life's ingredients directly to the surface of our young world. The building blocks of life weren't necessarily forged exclusively on Earth. They were already part of the cosmic inheritance, a gift from the chemistry of interstellar space. This means the potential for life is not a rare, fluke occurrence limited to planets with just the right atmospheric conditions. It is written into the fundamental chemical processes of the galaxy. Wherever a new star and planetary system form from such an enriched cloud, those planets will be seeded with the same basic chemical toolkit. The universe, it seems, is hardwired for chemistry that leads toward complexity. The vast cloud of alcohol in Sagittarius B2 is far more than a celestial curiosity. It is a testament to a universe that is not just habitable, but actively, prolifically prebiotic, setting the stage for life wherever the conditions allow it to take hold. But if the universe is so proficient at brewing the chemical precursors for life, it raises a far deeper, more metaphysical question. Could the cosmos itself be alive, or at the very least conscious? This brings us to one of the most profound and controversial truths of all. The universe itself might possess a form of consciousness. This isn't about a giant, cosmic brain thinking human thoughts. It's the radical idea that consciousness might not be a rare and recent product of complex biological computation, but a fundamental, irreducible property of the universe, as basic as mass or charge. This theory, known as panpsychism, suggests that mind and matter are inextricably linked, and that some form of subjective experience might be present in all things, from a human being to a photon. The standard scientific view, known as emergentism, argues that consciousness is like wetness. A single water molecule isn't wet. Wetness is a property that emerges only when a vast number of molecules are gathered together in a specific way. Similarly, consciousness is thought to emerge from the incredible complexity of the brain's neural network. But this view faces a formidable challenge: the infamous hard problem of consciousness, articulated by philosopher David Chalmers. The hard problem asks why and how physical processes in the brain give rise to subjective, qualitative experience. Why does the firing of Chinese letter neurons feel like the taste of chocolate or the color red? We can map every neural connection, but we can't seem to bridge the gap between objective electrical activity and subjective inner life. Panpsychism offers a potential solution. Consciousness doesn't emerge from complexity, it was there all along. It's a fundamental feature that the universe is built from, and complex systems like our brains don't generate it, they simply amplify it, channel it, and give it a richer, more complex form. This idea finds some startling, if speculative, resonance with the bizarre world of quantum mechanics. The central mystery of the quantum world is the role of the observer. As we saw with the double-slit experiment, particles seem to exist in a blurry cloud of possibility until they are measured, at which point they snap into a definite state. This has led some prominent physicists like John Archibald Wheeler and later Sir Roger Penrose to propose that consciousness itself might be the mechanism that collapses the wave function. In this view, the universe only becomes concrete and definite through the act of observation by a conscious entity. It's a proposition that places mind at the very center of physical reality, not as a passive byproduct, but as an active participant in bringing the world into existence. While this remains a highly contentious interpretation, It highlights the persistent and puzzling connection between information, observation, and reality, a connection that panpsychism attempts to address head-on. Another angle comes from information theory, which suggests that the universe might be fundamentally made of information, not matter. If reality is at its root a kind of cosmic computation, then consciousness could be the subjective experience of that information being processed. Think of the universe as a colossal, self-processing network of data. In such a framework, even the most basic systems are processing information. A single electron, for instance, is responding to the electromagnetic field around it. It's taking in information about its environment and reacting. Panpsychism, in its most modest form, simply suggests that where there is information processing, there is also a minuscule grain of subjective experience or proto-consciousness. A rock would have an unimaginably simple and dull experience, perhaps akin to a single, timeless binary bit of feeling. But a human brain, with its 86 billion neurons forming a network of unimaginable complexity, would weave together countless tiny grains of experience into the rich, flowing tapestry of thought, emotion, and sensation that defines our lives. The implications of this are as vast as they are strange. It suggests a universe that is not a dead clockwork mechanism, but is in some sense awake, or at least simmering with the potential for experience. It offers an elegant, if unorthodox, solution to the hard problem. Consciousness isn't something that mysteriously appears from non-conscious stuff because there is no non-conscious stuff. It was there from the very beginning. This view also re-enchants the natural world, not with gods or spirits, but with a deep, intrinsic interiority. It proposes that every interaction in the cosmos, from the fusion of atoms in a star to the orbit of a planet, is accompanied by some faint, elemental form of feeling, a whisper of experience utterly alien to our own, but experience nonetheless. Of course, panpsychism is fiercely debated. Critics argue it is untestable, that it merely pushes the problem of consciousness down to a smaller scale without solving it, what's known as the combination problem. How do billions of tiny bits of proto-consciousness combine to form my single, unified awareness? Furthermore, it seems to violate the principle of parsimony, or Occam's razor, by attributing a complex property like consciousness to simple particles. Yet, its proponents counter that emergentism has its own combination problem, struggling to explain how non-conscious particles suddenly give rise to consciousness when arranged in a certain way. They argue that panpsychism might actually be the more elegant solution, weaving consciousness seamlessly into the fabric of physical law from the start. Whether a profound insight or a philosophical dead end, the idea that the universe might be conscious forces us to confront the deepest mystery of our own existence, challenging the very boundary we draw between the inner world of the mind and the outer reality of the cosmos. Now, if the idea that the universe itself might possess a form of consciousness feels like the ultimate stretch of our imagination, our next truth takes that concept and projects it onto a cosmic screen, suggesting that everything we perceive might not be base reality, but an elaborate, artificially constructed facsimile. Truth 29 presents one of the most debated and mind-bending ideas of the 21st century. We could be living in a sophisticated computer simulation, and this simulation hypothesis is not just a plot from a science fiction movie, but a serious possibility being considered by prominent physicists, philosophers, and technologists. The argument for this staggering idea was most famously formalized by the philosopher Nick Bostrom of Oxford University. His simulation argument doesn't claim that we are in a simulation, but rather that at least one of three propositions must be true. The first is that almost every civilization at our level of technological development goes extinct before it becomes capable of creating realistic simulations. The second is that even if they survive, advanced civilizations have virtually no interest in creating such simulations. And the third proposition is that we are almost certainly living in a computer simulation. Bostrom's trilemma forces us to confront a logical chain of reasoning. If it is possible for a civilization to reach a technological level where it can run vast numbers of highly detailed simulations of conscious beings, ancestor simulations, as he calls them, and if such a civilization has any desire to do so, then the number of simulated minds would quickly and vastly exceed the number of original biological minds. Therefore, from a simple statistical standpoint, any conscious being, yourself included, is far more likely to be one of the simulated ones than one of the original biological creators. This isn't just philosophical musing, it connects directly to our trajectory in computing. We are already creating increasingly immersive virtual realities. Video games have evolved from simple pixels to sprawling open worlds populated by non-player characters with basic artificial intelligence. With the rapid advancement of virtual reality, augmented reality, and neural interfaces, it's not a giant leap to imagine that a sufficiently advanced civilization could create simulations indistinguishable from reality for the conscious beings within them. If the trend of exponential growth in computing power continues, be it through quantum computing or some other paradigm, then the computational capacity to simulate an entire planet or even a universe might not be a physical impossibility for a civilization that is thousands or millions of years more advanced than we are. Some scientists have even proposed ways to test the simulation hypothesis. One idea, put forward by physicists like Seeler's Bean, suggests that if our universe is a simulation, it might be running on a finite computational resource like a cosmic lattice or grid. This underlying digital structure might impose a fundamental limit on the energy of particles, much like a computer screen has a resolution limit. We might detect this by looking for a cutoff in the energy spectrum of ultra-high-energy cosmic rays. These particles, which travel from distant galaxies, should not have an inherent energy limit according to standard physics. But if they consistently top out at a specific energy, it could be a sign that we've hit the processing limit of the simulation. Another potential glitch could be found in the constants of nature. If a simulation is programmed, its constants might be perfectly round numbers or exhibit patterns that wouldn't occur in a purely natural, physical universe. So far, our measurements of constants like the fine structure constant show no such obvious signs of digital engineering, but the search for anomalies continues. Of course, the hypothesis faces fierce and compelling criticism. The most obvious challenge is the sheer computational burden of simulating an entire universe down to the quantum level for every conscious being within it. The energy requirements would be astronomical, perhaps physically impossible even for an ultra-advanced civilization. However, proponents counter that the simulation wouldn't need to be perfect or complete. It could be like a video game that only renders the parts of the world that are being observed. This physics engine would generate detail only when needed, a principle eerily similar to the quantum mechanical notion that particles don't have definite properties until they are measured. Furthermore, if the simulating civilization has mastered physics at a level we can't comprehend, they may be using computational principles that make such a feat trivial. The implications of the simulation hypothesis are profound, touching on everything from ethics to the meaning of life. If this is a simulation, then the laws of physics are not fundamental laws of nature, but merely the rules of the simulation, the programming code. The programmer would occupy a role similar to a god, having created our reality. It could provide a potential solution to the problem of fine-tuning the universe's constants are perfectly set for life, not because of a multiverse, but because they were deliberately chosen by the programmers. It also raises existential questions. Does our lives have less meaning if they are simulated? Most philosophers argue no. Our experiences, our joys, and our sorrows are just as real to us. The pain you feel is real pain, regardless of whether the neurons firing are biological or lines of code. The hypothesis doesn't necessarily devalue our existence, but it radically recontextualizes it, suggesting that reality is a much more plastic and malleable concept than we ever dreamed. Whether a provocative thought experiment or a genuine description of our cosmos, the simulation hypothesis forces a monumental shift in perspective. It challenges us to consider that the deepest truth of the universe might not be found in galaxies or quantum particles, but in information, computation, and consciousness itself. It represents the ultimate convergence of technology and metaphysics, an idea that we are only beginning to grapple with as we ourselves take the first tentative steps toward building simulated worlds. And this brings us to our final and perhaps most staggering truth of all, a concept that pushes the very limits of human comprehension and forces us to confront the ultimate scale of reality. Truth number 30, the universe might be infinite. This isn't just a poetic turn of phrase to signify vastness. It is a serious cosmological possibility with evidence to support it, and implications so bizarre they redefine the words everything and everywhere. For centuries, the question of whether the cosmos is finite or infinite has been one of philosophy's greatest puzzles, but today we have scientific tools to probe this deepest of mysteries. Our most precise measurements of the universe's geometry, primarily from the detailed maps of the cosmic microwave background made by the Planck spacecraft, point to a startling conclusion: the universe is flat. Now, this doesn't mean it's shaped like a sheet of paper. It means that on the largest scales, the rules of Euclidean geometry we learned in school hold true. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. This finding of a flat geometry is crucial because it directly relates to the universe's overall density, and by extension, its fate and its size. In the framework of Einstein's general relativity, the geometry of the universe is determined by its mass-energy density. If the density is greater than a specific critical value, the universe would have positive curvature like the surface of a sphere and would eventually collapse in a big crunch. This would be a finite, closed universe. If the density is less than the critical value, the universe would have negative curvature like a saddle and expand forever, an open universe. But our measurements show the density is almost exactly equal to the critical value. The universe appears to be perfectly flat, or so nearly perfect that we cannot detect any curvature. A perfectly flat universe in this model has to be infinite. It has no edge, no boundary, and it extends forever in every direction. Now, the universe we can see is most definitely finite. The observable universe is a sphere centered on us with a radius of about 93 billion light-years, containing all the light that has had time to reach us since the Big Bang. But this is just our horizon, our cosmic island. Beyond that horizon, the universe almost certainly continues, and if it is flat and infinite, then it continues without end. There is more space, more galaxies, more of everything forever. This leads us to the first truly mind-breaking implication. If the universe is infinite and the laws of physics are the same everywhere, then every possible event that can happen must happen. In fact, it must happen an infinite number of times. This is a consequence of probability played out on an infinite canvas. In an infinite universe, there is only a finite number of ways particles can arrange themselves within any given finite volume. But with infinite space, those finite arrangements must repeat over and over again, endlessly. So let's start with something simple. Somewhere, impossibly far beyond our cosmic horizon, there is another galaxy exactly like our Milky Way. Around a star exactly like our Sun, there is a planet exactly like our Earth. On that planet, there is a country exactly like the one you live in, a city exactly like yours, and a street exactly like yours. And in a house on that street, there is a person who looks exactly like you, reading a script exactly like this one at this exact moment. In fact, there isn't just one. There are an infinite number of them. For every decision you've ever made, there is a version of you out there who made a different choice. A version of you who took that different job, married that other person, or bought a different brand of cereal this morning. Every historical event that could have unfolded differently did so somewhere else. There are worlds where the Roman Empire never fell, where dinosaurs still rule the Earth, and where you are the absolute emperor of the solar system. But the infinite doesn't stop with mere variations of our world. It generates realities so alien they defy all description. There are planets made entirely of sentient crystal, civilizations that communicate in smells, and regions of space where the laws of physics are just slightly different, not by evolution, but by pure random chance in the arrangement of particles. In an infinite universe, anything that is not strictly forbidden by the laws of physics is not just possible, it is guaranteed, and it exists right now in a place we can never hope to see or visit. This idea is simultaneously terrifying and liberating. It can make our lives feel insignificant, a single identical copy in an endless sea of duplicates. But it can also be a source of profound wonder. It means that every moment of beauty, every act of kindness, and every great human achievement is not a fleeting spark in a dark void, but an eternal pattern repeating forever across the infinite cosmos. Our story, in all its forms, is forever written into the fabric of an endless universe. It is the ultimate conclusion to our journey through these surprising truths, revealing a cosmos whose true nature is more magnificent, more bizarre, and more humbling than we could have ever possibly imagined.